Yeah, we had like 10 people sign up yesterday. So
Okay,
probably we should blast out again.
that sounds totally reasonable. I can handle that.
Yeah, we had like 10 people sign up yesterday. So
Okay.
probably we should blast out again.
Pavvel, I'm going to put the YouTube link in the Zoom chat right now.
Perfect.
It is live.
I at least put the link up somehow, but I'm gonna figure out how we did it last year because we probably had a good scheme.
I'm just going to send the same email I sent yesterday with starting soon.
Yep, I think that's fine. Okay.
Son of a. I have to get done.
I think GitHub changed how GitHub Pages works, and as a result, deploys take a lot longer now, which is a bit of a bummer. But we are now up. There's a banner on the main page and a live stream link on the schedule. And Jean-Michel asked me to post his slides, but only after his talk. So I'm going to get ready to bring those up.
Hello.
Hey, Fredrik.
Hi.
And Pavvel, I realized I didn't do an AV test yesterday. So
Oh yeah, let's check that your slides work.
let's check out my slides too.
Those look good. Can you go back forward? All right, that looks good.
It's not showing up in our local projector here. I guess the people in the room and at UW will just have to deal with it not being on the projector.
Hmm.
I didn't realize you were back at UW, Zach.
Yeah, PLDI is settled, and so life is good again.
Are you?
I mean, PLDI was fantastic,
Summer?
but it was a lot of work.
Where was PLDI?
In Seoul.
Ah, okay.
Yeah, it was an adventure.
Well, good food in Seoul, though.
Absolutely. Samir, I have on my list for us to grab coffee or something.
I was
And
actually just thinking about it today.
Yeah,
Now that you're back, I will make time and come over.
yeah, that would be so much fun. We can do lunch or go with the students to the ab or something.
Yeah,
Bit
that'd
of
be great.
both. Yeah, I think we'll figure something out.
So Zach, one thing you might want to check is I think you have the YouTube open in another tab,
Okay.
and that's making a tiny thumbnail of the slides appear in the bottom of your screen.
I can just close that arc preview and I
Yes,
don't think it'll break anything.
it won't. It'll pause the YouTube video, but I think that's fine. Yeah, I think if you had gotten started, it would have been weird because it would have been a slide from like 5 minutes ago.
Okay.
Okay. I know on the schedule we said 7:50, so hopefully people join roughly by then.
Well, they might be used to the normal FP bench standard of 5 minutes of
5 minutes.
shooting.
Yeah, I was gonna say we can also wait a little bit past the exact starting point.
I'm also just for paranoia going to record to my machine.
Yeah, good idea.
But the YouTube should also be recording.
Do we have an FPTalks Slack channel this year?
Pavvel and I chatted about this, and I think that we are just going to use the Zoom chat, just have one fewer thing.
Gotcha.
It's a bit of an experiment. The threading in Slack is really nice, but getting everybody to make another account is sort of a lot. And so if we can get away with just the Zoom chat, I think would be optimal. But we'll see what happens.
Yeah, I think just having one fewer piece of software to manage is an underrated win. All right, that's great. We've got folks joining us, so I think we'll be good to start a minute or two past the schedule time in keeping with tradition.
Actually. I think for the emceeing, I will switch my video to the laptop. Maybe wait another minute, Pavvel, you think? I mean, it's
Yeah,
also not going to
I
take
think we're
me
pretty
10
much
minutes to do the
good to
intro.
go.
So
Yeah, I think we're good to go anytime.
are all the session one people are here?
That's actually what I was just checking. Yes.
Okay. Well, in that case, let's kick things off. Welcome everybody to FPTalks 2025. We are very excited that everybody is getting together to talk about numerics and floating point algorithms, hardware, etc. We have another fantastic lineup this year of 11 speakers covering all kinds of different aspects of numerical computing, everything from hardware design to retrospectives on floating point broadly. Of course, being 2025, there's a lot of perspectives on ML and questions about getting floating point to work with LLMs. But one thing that has been constant, this is the biggest FP talks we've ever had. So every year it's the biggest one ever. This is the 6th time in a row, which is pretty exciting. And for folks who are joining for the first time, who maybe haven't been to one of these before or heard of the FP Bench organization or the FP Talks effort. The reason we're here is to serve as kind of a water cooler for the floating point research community. So I don't know about you, but at the University of Washington, there's a lot of amazing people that are excited about a lot of things. But sometimes when you say floating point, their eyes glaze over a little bit. So this is a place for everybody who gets really excited when somebody starts talking about addition or multiplication or an FMA or some other numerics thing. And gives a place for people with this particular niche interest to connect and build a community and grow. On top of that, sort of being just a place for people to hang out and talk about all these topics we're really excited about. We also have put a bunch of effort into building the community and also trying to provide various resources to support research in this space. And all of these are available at fpbench.org. So if anything sort of flies by too quickly during the intros or whatever, you can always check that out or subscribe to the mailing list and kind of stay up to date with what's going on. So very briefly on the community side, we've really sort of settled into this routine of 2 major events that regularly happen as part of the FP Bench community effort. One is that we have a talk every month for about an hour, and these tend to be extremely lightweight, informal, more of a chat, a discussion. We really welcome demos, and these are a great opportunity to kind of explore stuff going on in the community, sort of ongoing or current work, exploratory, new projects and ideas, etc. We also have this annual workshop, which you are in right now. So congrats, you've already made it here. And this is often shorter talks where we're not doing interruptions during the talk, but we will have time to have discussion during breaks in between. And these are more typically for announcements of big things that have happened or retrospectives, exciting new efforts, etc. On the resources side, there are several things that FPBench provides. We have a fairly large benchmark suite, which is pretty stable. It's been used in dozens of papers, has different notions of metrics for making fair comparisons across tools, which is tricky because different floating point tools are targeting different goals. And so having some kind of standardized metric is helpful. We also maintain sort of directories of different floating point tools, educational resources, and we also have sort of standards for describing interchange formats so that people building numerical tools focusing on different aspects of accurate and fast numerical computing can collaborate and ideally compose tools to build end-to-end pipelines. So there's sort of this range of things that are available, and it's all open source online under permissive license, very industry friendly, and we welcome PRs. So lots of opportunities to get invited there. If you're curious, please ask anybody from the FPBench org how to check more of that out. So that's really sort of the big picture about what FPBench is. It's this community effort, providing some infrastructure and resources, and trying to have sort of a clearinghouse for ideas, but also a meeting point for people who might not have somebody down the hall that's really excited about interval arithmetic or the next new numeric standard. So for today, we're going to have a bunch of fantastic talks. In session one, we're going to go from 8 to 9. And then we're going to take a break from 9 to 9:30 where people can discuss, repeat that same recipe again from 9:30 to 10:30, and then from 11 to 12, basically wrap up. And during the conclusion, unfortunately, one of our speakers had a family emergency and couldn't make it. So in that last 15 minutes, we'll also have an opportunity, if people want, to do a little bit more of a discussion about FPBench community, etc. On the logistics side, please mute your microphones so that during the talk, only the speaker is live, is being recorded. Also, if you have any questions, please put them in the Zoom chat, and then I will help session chair and run the Q&A. You are welcome to ask your question live in person. I'm also happy to read questions if you don't feel comfortable doing that. Just to note, the talks are being recorded and live streamed, so heads up about that. You can always go to the YouTube link if you prefer to not be directly recorded. Also, we are operating under the ACM Code of Conduct. If anything comes up, you can email the FPBench advisors list, which was in the registration response email, or just email me, whatever is easiest for people. So I think with that, we are basically ready to go ahead and get started a couple minutes early. Here's the first session, and we're really, really excited to kick things off by welcoming Jean-Michel Muller from CNRS to talk about some thoughts on floating point. So I think with that, unless I've missed anything, Pavvel. Okay, having gotten the thumbs up, I think with that, I will go ahead and stop sharing and let Jean-Michel take it over.
Okay, just let me. Do you see my slides? Okay.
Looks fantastic.
So, good morning or good evening, depending on where you are. I wanted to share a few thoughts with you on what we should build, require, specified, standardized in floating point arithmetic in the future. The main goal is to preserve consistency and to preserve portability, reproducibility of software as much as possible, of course. So 44 years ago, Kahan published a paper, Why Do We Need a Floating Point Standard, where there was that table that describes various systems that existed at the time. And it shows that there were many vastly different floating point environments, different radices, precisions, ways of rounding or ways of handling or not handling exceptions. And some of these systems, in fact, were pretty good, but many were quite poor. And this diversity led to an extremely poor portability of numerical software. And furthermore, it was almost impossible to prove anything. A proof needs to start from something, to start from assumptions. And what can you prove if you don't even know what an addition does? So then came the IEEE 754 standard, and at the beginning it just defined two formats, single precision and double precision, and the way operations are rounded. And this already was a great advance, because just from correctly rounded operations, you can deduce that you have a uniform bound on relative error of the operations. And this is the key to clean and rigorous numerical analysis since Wilkinson. The standard also defined the way exceptions should be handled. And just because of that, of these requirements, the jungle I just described became a well-kept garden. Well, with some, I am a bit exaggerating, there were still strange things. For instance, the presence of the extended formats, mainly the double extended format, had good and bad consequences. Generally, you had more accurate calculations, and the presence of extended formats frequently allowed to avoid spurious underflows or overflows in intermediate calculations. But there were bad side effects. Double roundings first, and the fact that it was quite difficult to predict the accuracy of a calculation. Depending on whether the intermediate results are stored in 80-bit registers or 64-bit memory, you could have quite different results. Also, probably linked with these extended formats, there's the curse of this C-long double data type, which is not a data type in a way. You can have so different things. But anyway, IEEE 754 has been a great progress in numerical computing. And something that helped that progress was the fact that in the 80s, there were not so many application domains. Essentially, we had numerical simulation and financial calculations. Now, the situation is quite different. We have plenty of application domains. We still have numerical simulation and financial calculation, of course, but we have games, entertainment, machine learning, embedded computing. And these domains have extremely diverse requirements and characteristics. In terms of speed, need for reliability, accuracy, dynamic range, provability, reproducibility, and so on. So these are extremely diverse. The other big change, but everybody knows that, is the fact that the ratio of the time to read or write in memory over the time to perform the operations has increased a lot since the 80s. And this is a strong incentive, of course, to use small formats whenever possible, even for applications that need much accuracy at the end. Also, we have some heterogeneity of the computing platforms, but this was already the case in the 80s, in fact. So it seems that we are back to the jungle. You know, this table gives characteristics of some of the formats that either are implemented or are proposed at the present time. And this table is not so different from the other table. It seems we are back to some chaos. What can we do to avoid complete chaos, in fact? Well, specify, and specify in a way. We need to think about how we can help interoperability between these various formats. And I will come to that later on, but we must have more than one application in mind, even when we think we are designing a format or an environment just targeted at one application. And we need clear, simple, and complete specification of everything. There is a lesson to be learned from the domain of design thinking. Those who design chairs, they know that they will also be used as step ladders. Well, these careless users, you can decide you call them idiots, but they are there anyway. They will be there. So it's best to take this use into account when you design a chair. And it is the same for us. In fact, there is nothing such as an arithmetic format operation dedicated to one application. If it's fast, other people will use it anyway. Just think of the success of mixed precision computing. The very small formats that were targeted at AI only, people use them for numerical analysis, and they are not idiots. It's a good idea in many cases. There's nothing such as a purely storage format. Some will do arithmetic with it. At the beginning, FP16 was thought to be a storage format only. There's nothing such as an extended format that only serves for implementing functions for a corresponding basic format. So we must think about other applications, not only about the applications targeted by the environment we are designing. And some applications, some other applications need uniform relative error bound. For instance, error control in numerical analysis. This rules out the systems that do not guarantee a uniform relative error bound. And also, some applications need the possibility of formal proof, for instance, applications in avionics and automated transportation, and therefore a full, clear, precise specification. We must carefully consider this. Also, I would like to talk a bit about correct rounding. There are in tensor cores, there are many matrix operations of that form, AB plus CD plus something and similar. If they are not fully specified, it will be quite difficult to prove anything. And a lack of specification will undermine all portability and reproducibility efforts. A specification must endure over time if we want software usability. And I really think that the only specification that can stand the test of time is correct rounding. And for example, we have a paper in ARWITH 2024 that shows that with a correctly rounded AB plus CD plus E, for instance, you can do many, many very interesting things. You can Google that paper if you wish. I strongly believe that the same holds for the most fundamental elementary functions, such as exponential, log, sin, and cos. Again, we have a recent paper to appear in ACM computing surveys. Just Google it and you will find it. And I will finish with mixed precision computing. It's not just a passing trend, it's here to stay. Because in all complex enough numerical calculations, many parts do not need the same precision. For instance, the initial steps in iterative algorithms can be done in very small precisions, in fact. So these applications, we use various different formats, and we must facilitate interoperability between these formats. For instance, this can be done by providing round to odd in the wider formats to avoid double rounding issues. Maybe we should promote consistency between ranges by generalizing the FP32 versus bfloat 1680. That is, to have for a given word length W, beyond the standard format of length W, an accurate or a high range version with the exponent range of the next widest format, maybe. And also, I insist on that. It's important for mixed precision. A numerical analyst needs to know what a 16-bit tensor core actually does without having to do reverse engineering. By the way, full reverse engineering is totally impossible given the number of input arguments. Again, clear, simple, unambiguous specifications are essential. And I think that's it. Thank you very much for your attention.
Thank you so much for the talk. Just to remind folks, please put questions in the Zoom or raise your hand and we'll pick on you and call you out. We've got time for a couple questions before we need to tee up the next talk. So one thing I was curious about, Jean-Michel, really enjoyed the talk. You emphasized sort of correct rounding as the bedrock test of time property that these numerics can and should provide. What happens with things like block floating points, though, where maybe you have a shared exponent across multiple values, or maybe other trade-offs, challenges to correct round? Like we have a talk later today on random rounding, or I've seen also people show huge area improvements in chip design with just faithful rounding. I was wondering if those are corner cases or if we should avoid those designs because correct rounding is difficult to specify or provide.
Yeah, correct rounding is probably difficult to specify in this case, but we should put an effort of specifying something of the same kind in these cases.
Got it. That makes sense. We also have a question from Ganesh here in the chat about consistent. Oh, Ganesh, do you want to?
Yeah, since Jim is there, I'll ask Jean-Michel and Jim. Yeah, consistent exception handling is something that Jim has promoted, and I think some thinking is needed. What are your thoughts?
Yeah, clearly. I agree.
So given the weak semantics of what NANDs do or don't do, our notion of consistency was watered down a little bit, but I think it's still worth it, even if it's not, doesn't take advantage of all the bits that are available in a NAND.
Related follow-up is different software or hardware seem to coerce exceptions in different ways. I'll just leave it at that. Yeah.
I see a question. Okay, excuse me.
Oh, no, you're fine. Yeah, exactly. Yeah, Pavvel has another question.
Yeah, I wanted to ask, we kind of see like an ebb and flow of whether this hardware is standardized. There was a time when GPUs didn't do IEEE basic arithmetic, like addition, multiplication, division. These days they do, but these new units, they're not particularly standardized and they often do non-standard things with, flush to zero or whatever. Do you think it'll flow back to standards? Do you think ultimately that's what's going to win? Or do you think this ebb and flow actually shows that the hardware is more complicated and people are willing to do non-standard things?
Of course, if we want to be more accurate, if we want to do things cleaner, there is a cost. But I really think it's worth paying the cost. If you remove the brakes from your car, it will go faster because it will be lighter.
We also have a question from Montas. Montas, do you want to come on and ask, or I'm also happy to read it?
Yeah, I was wondering if some people look at correct rounding as very expensive for dot products and matrix multiply and summation. What about standardizing the ordering of operations and internal precision? Is that doable?
Some summation algorithms are based on a clever choice of ordering. So if you impose some ordering, you may have them in trouble. I know Jim does things differently to guarantee reproducibility. And with his algorithms, ordering is not important, but some will try to do some ordering. So I'm not sure it would be a good idea to standardize some ordering, but maybe I'm wrong. I just want to point out that we must think about these things. Not just say, I build an operator that computes, well, approximately that. It's too dangerous.
Okay, thank you very much.
Okay, I think that with that, we're going to go ahead and move on to the next talk. So Theodore, if you want to share screen, make sure everything still works. So Theodore Lindberg is from Linkoping and is going to talk to us about flexible data types for finite word length simulations in Python.
Yeah. Hello, can you hear me?
Yeah, please take it
Great.
away.
Yeah. So I'm here to present APyTypes, which is a new Python library that we've been developing for almost 1.5 years now. So typically, algorithm design starts in software using single or double precision floating point. But at some stage, you want to implement your design on specialized hardware. And one of the most important questions becomes, what word length should you use? Because you don't want to use double precision floating point necessarily. Instead, you want to use short data types that are specific for your implementation. But with shorter data types, the quantization errors and the dynamic range becomes more apparent. So we want to simulate these effects, but doing so using RTL simulators is error-prone and slow. And ideally, we want to determine the data types before spending our time implementing things in hardware. So this leads us to the need for bit-exact simulations in software, where we can perform iterations fast. We also note that Python has become very popular, especially with NumPy and SciPy being popular open source projects. There are some existing solutions. For example, for C and C++, there's APyTypes and ACtypes. These are fast, but requires recompilation when you want to make changes, and also not that interactive when you want to plot data. A bit more interactive is the Python libraries, for example, FXP Math, which is a Python library for fixed points, supporting arrays, but it's a bit slow being completely in Python. Then there's GMP2, which is great for arbitrary precision, but only supporting scalars. And then there's MLD-type and NP-torch for machine learning. These are great if you know you're going to use, let's say, bfloat 16, but otherwise you're a bit limited on the selection of types. So we bring APyTypes for bit-exact, custom, fixed, and floating point formats, supporting scalars, arrays, and complex types. The backend is written in C++ for some performance, and one of the design goals is that it's tailored towards people who design algorithms and digital hardware. What it means is that the simulations should be bit accurate, that the internal representation stays true to the hardware implementation, and yeah, it should have some features that makes it convenient to use. Being a Python library, we want to integrate well with the already rich ecosystem. So this means having conversions to and from NumPy arrays, being able to use it in CocoDB test benches, and so on. So this is an example to give you a feel for the library. I see a couple of authors here in Zoom, I think. So let's say we have this ordinary differential equation, and we're using forward Euler with a certain number of iterations and a certain subsize. And we wonder what are the effects when using different floating point formats and different rounding or quantization modes. Not a perfect example, but it will show some features of the library. So we start writing our Python program, importing our library, taking the number of iterations, the step size, the number of exponent bits, the mantissa bits, and what quantization mode to use. We set up our system. This ODE matrix is a 2x2 array, initialized from just a Python list, and you specify your floating point format. And we also allocate our results variable, which will just initialize to 0. So very similar to how you would set it up in using NumPy. Some more setup, and now we want to perform all the calculations using our rounding mode of choice. So we create this context in which all the arithmetic inside this code block will be using the quantization mode we choose. So here are the operations. In each iteration, we perform a matrix multiplication using the @ operator, add it to our current value, and store it back into the results. And this results variable, although it's an array of our custom floating point format, you can use it directly to plot using matplotlib. So here's the reference using binary 32, using round to nearest ties to even. And yeah, so it's basically the unit circle. But what happens if we're using binary 16? We get these interesting effects. But using stochastic rounding, we see that this red dotted line is quite close to our reference. But of course, we're not limited to the classical selection of types. We can use something more exotic, for example, some FP14 format, which is the green dotted line. We define the floating point format in APyTypes by the number of exponent bits and mantissa bits and the bias. And by default, the bias will be an IEEE-like bias. So this is a generalization of the IEEE 754 standard. So all the floating point objects support not the number, subnormals, and infinities. To instantiate an object, you can create it from an integer or a Python float. And you can also create it from an integer bit pattern, or you can set the fields individually. The resulting floating point result will be the same format as its input, but we also support operations with mixed formats, and how that works is documented. Also supporting arbitrary fixed point numbers. I'll just mention it quickly here. You can create it from a float again, or from a bit pattern. But here the word lengths are determined statically and increased at each operation. So you never get overflow and you never get quantization, unless you want to do so, and then you do it explicitly, saying what format you want to have and what quantization mode and how you should handle overflow. These classes also have custom arrays. So you can create it from a nested Python list, or you can create it from a NumPy array. And we support the at operator for matrix multiplication, multi-dimensional transposition, mixing arrays and scalars. And then there are some convenience functions like slicing, broadcasting, and like I mentioned, you can plot it directly using matplotlib. Since recently, we also support complex data types. For floating point arithmetic, the intermediate results are quantized, so following the C99 guidelines. And yeah, for some fine-grained control, we also have some context handling. So using the quantization context, you can change the quantization mode. And we also have accumulator context. So if you want to perform a matrix multiplication, you can do so using a wider accumulator to store the intermediate results. There's currently 15 different quantization modes, so plenty of modes to choose from. And yeah, written in C++, like I mentioned. It is cross-platform, supported on the 3 major platforms. Where possible, we try to leverage native SIMD features using Google Highway. And in the future, we want to have some more floating point customizability, being able to turn on or off infinities, turning off some normals, etc. Having unsigned fixed point numbers. Currently, they are 2's complement. And then generating like memories for VHDL or Verilog, and supporting more like NumPy functions. So if you're interested, please try out the library, and you can submit issues, and pull requests are welcome as well.
Fantastic. Great work. So folks, just a reminder, please drop questions there in the chat. One thing I was curious about from this, you mentioned doing these mixed precision or even mixed format, mixed type operations. How do those work? Is there some notion of always cast to the higher precision and cast back down? Does that work uniformly?
Yes, so the approach we have is that the resulting format will be like the maximum number of exponent bits of its input and the maximum number of mantissa bits of its operands. And the bias, since you can set the bias to basically anything, the resulting bias will be like the average, so to say.
I see. And then maybe following up on that, if I wanted to, you showed sort of, which is great for a talk, this notion of measuring error like by plotting essentially and seeing the different behavior under different word lengths. Is there a general notion of error you can use as a sort of baseline as you're doing this sort of design space exploration across different parameters for your number system?
Like ULP, you mean? Like,
Or yeah, although ULPs are tricky because what an ULP means depends on the format. So if you're doing mixed format, that's a little bit dicier, I think.
Yeah. Yeah, I don't think we have anything like that.
No, totally.
Understand.
The other thing, sorry, I feel like I'm just peppering you with questions. I like this line of work a lot. I think it's really cool. I don't know if you're familiar with Theodore Omskit's Universal Library. So
no.
it's yeah, I'll drop a link in the chat, but he gave a talk here a couple years ago for trying to build a framework to provide a bunch of different number systems, but a lot of it through C++ templates. I think a lot of users are probably happier with the NumPy integration and using Python. So that's really cool. Maybe one last question. Oh, it looks like Pavvel has one. Okay, I have another one, but let's let Pavvel go.
Thanks, Zach. I know you got a lot of questions. Yeah, I sort of a variant of that is like, have you thought about extending this to other sort of variations on floating point? So like block floating point for the NumPy arrays, potentially posits or something else like that. Do you see that as being a direction you want to go?
We've talked about adding like posits and other floating point variations, but not until they become even more popular. So for now, it's like IEEE like formats. Yeah, but we aim to have like being able to turn off infinities and turning off subnormals. So that's
cool.
Zach, would I be able to jump in with a question?
Yeah, Ryan, please go for it.
Awesome. Theodore, while you were developing or have you been in the process of developing this library, have you come against sort of an adversarial use case, which is at every single operation, you might be interested in switching context in some way, shape, or form, or maybe it's format as well. Have you stumbled upon such a test case?
Not personally, but I know at least for the fixed point part, it's more like you want to track, if you add two numbers, the word lengths will increase, and you want to track the different word lengths at each operation. And yeah.
I see. Thank you. I'm sort of imagining this case where as sort of a search optimization problem, one might want to schedule a different width or mode for each particular optimization, for each particular operation. So I didn't know if that was something that you had thought about supporting or had even come up as a
but it's doable to cast to different formats and perform operations with a particular format briefly and then switching to a different format or switching back and forth. So it's doable.
Very cool. Thank you.
Yeah, thanks so much, Theodore. There's a few more comments popping up in the chat down here, but I think we will go ahead and start transitioning to the next speaker. So Fredrik, if you could see if your screen share works.
Yeah. Let's see.
Fantastic. So up next, Fredrik's going to tell us about making floats faster by making them more vector friendly. So I think with that, Fredrik, please go ahead. Also, for people who don't know, Fredrik has an amazing array of headshots on his website. You can get pretty amazing ones by refreshing the page. So with that bit of trivia aside, Fredrik, please take it away.
All right. Thank you very much. So basically, we're interested in multiple precision floating point arithmetic, which we're using for various things in the Flint library. And my goal for this project that I worked a bit on basically in the last year is to have a replacement for MPFR or Flint's very similar ARF type for more efficient arithmetic when we consider vectors where all numbers have the same precision. So we consider standard radix 2 arithmetic, and I want to support a full word exponent because we have a lot of applications from computer algebra or number theory where we need very large or small numbers. So it's not always appropriate to use floating point expansions, for example. And I want to have a controlled relative error for the arithmetic. Personally, I'm not such a big fan of correct rounding. It's not really useful for most of the applications we have. It's not really a lot slower to support correct rounding, but it's more implementation work, and it's something I haven't done yet. Basically, the idea is that in most arbitrary precision types like MPF, MPFR, or ARF, you have a C structure of a fixed size that contains the exponent, sign, and precision with a pointer to an array of the words for the digits. And what we do basically instead is just to have a variable size data structure where we store the digits in line. So we have a kind of parametric type, and currently we go up to 66 words, which is kind of an arbitrary upper limit, which is basically just so that we can allocate and float variables on the C stack without risking overflow. So the most important arithmetic operation is multiplication. And sort of the heart of this work is something I did with together with Albin Olbeck, and which he presented at Arith earlier this year. Probably a few of you saw his talk. So we consider a product of two n-word integers, and we want to compute just an approximation of the high n words. So basically, by adding up the shaded rectangle here, we get an approximation. The shaded triangle here, we get an approximation with roughly n ULP error, and by including a few more terms, we get a fraction of ULP error. And then when we round to n words, then we get basically a constant bound for the error. So we considered optimizing this for 8664 and ARM64 using a combination of hard-coded base case multiplication routines and then a recursive algorithm for a larger n. So this is something that MPFR is using internally, for example. But in MPFR, the high multiplication routine just computes this dark orange part without the correction term, which means that you need one to convert the numbers to one extra word of precision internally, which slows things down a little bit. And by computing these correction terms, instead we get a slightly more efficient high product. So here's a comparison of the performance for high multiplication. The times are relative to MPN mol, so computing the full product using GMP. So n here is the number of words. So the black curve here, it's just the high product of arrays of words. And the blue curve is the n-float multiplication function, which does a few more things. It adds the exponents, it multiplies the signs, and it checks for underflow and overflow, and it also normalizes the significand to set the most significant bit if needed. So this is a little bit slower than just doing the operation on the word arrays, but not a lot slower. And you can see that we are quite a bit faster than MPFR's multiplication at any size. So here's another comparison of performance for arithmetic. So here we consider different operations on numbers with 2 words of precision. And I've included DD, so double arithmetic, just for comparison. So here we consider these operations on vectors of 100 elements, and we measure the effective performance in megaflops. So for addition, you can see nflot is quite a bit faster than ARF or MPFR or MPF, and about 1/3 of the speed of double arithmetic. It's also a bit similar for multiplication. For dot products, we perform relatively better compared to double arithmetic. So dot product is something that was already really well optimized for the ARF type in Flint. And this is important because it's a very important building block for things like matrix multiplication, polynomial multiplication, and so on. And nflot is basically using the same algorithm as ARF, but there's a little bit of overhead, a bit less overhead, so we can get a bit more performance. So if we increase to 4 words, so 256-bit precision, we also included a QD from the quad double library for comparison here. We get still a very nice speed up over MPFR and ARF for all the operations. And I was actually surprised to see that quad double performs so poorly, at least on my machine. But I should mention that this is not using any SIMD optimizations for quad double arithmetic. It's just calling the QD library. If we increase the precision a bit more, here looking at 8 words, we are less in the territory of overhead, and it's more about the speed of arithmetic, but still we have a nice speed up, roughly a factor 2 over ARF and MPFR. And if we go all the way up to 124-bit precision, still a nice speed up. I will talk a little bit about linear algebra. So basically, I think most of the time you don't really want to do floating point arithmetic if you can avoid it. It's usually more efficient to do fixed point arithmetic, certainly in an arbitrary precision setting. So basically, for linear algebra operations in Flint, we use, when possible, we use block recursive methods, where the idea is that we do direct floating point arithmetic just for the very small blocks, and for intermediate size blocks, where the size can be, it depends on the precision, but perhaps between 2 and 100, we convert to fixed point arithmetic, where additions are much faster, and we can benefit more from tricks like Strassen multiplication and commutative matrix multiplication algorithms, where we reduce to performing only about half the number of full precision multiplications. And then for very large blocks, it seems optimal to switch to a residue number system, where we basically linearize with respect to the precision, and we also can take advantage of vectorization for the mod P computations. The drawback is that when you work directly with the floating point arithmetic, you don't have to worry about how things are scaled, but when you convert to the blocks, then you either need to use higher internal precision, or you need to look very carefully at how the results depend on the inputs, so that you get similar accuracy. Basically, you want to emulate the floating point result using fixed point or integer arithmetic, which is something we do in Flint. And it's a bit tricky to get to do this optimally, and something I'd be happy to discuss with others here, maybe in the future. I think there are some interesting problems here. So my last content slide is just a comparison of performance for solving a 100 by 100 linear system. So the time is in seconds. Compared to various types, you can see the speed ups here. So we get, so for a real system between a factor 7 and 2 compared to MPFR, between 1.6 and 2.4 compared to ARF. And similarly for complex arithmetic, we get speedups between a factor 2 and 10 compared to the ACF type in Flint, which is just a pair of ARF, or the MPC type, which is a pair of MPFR. So the speedups here are basically a combination of two things. If I go back to the previous slide, basically the speed of the fixed point arithmetic here and the direct floating point arithmetic, where things add up. So some things I want to look at in the future are doing ball arithmetic in a similar way, and also combining with the SIMD acceleration. For example, by taking advantage of IFMA for single operations, or for using SIMD for the fixed point or RNS computation, or converting to floating point expansions. So thank you.
Wonderful. Thank you so much for the talk. There are some questions appearing in the chat. One question, I'm going to invoke privilege and jump to the head of the queue. You said combining with SIMD. I maybe misunderstood an earlier slide where you talked about having the special cases up to 9 that you sort of hand-coded in assembly. Those are not using SIMD?
Right. It's just using the integer operations on the CPU, just
So
serial
those are pure
multiplication.
scalar.
Yeah.
Interesting.
Yeah. Everything here is basically pure scalar.
And you don't think that GCC is parallelizing that for you?
No.
Very well.
No. So
right?
this is using assembly code, actually.
I see.
Yeah.
I see.
Yeah. I think basically the best way to do SIMD for arbitrary precision is to convert to either fixed point arithmetic or floating point expansions. You can do things with multiple precision floating point, but it's not going to be as efficient.
Right. Maybe while that's still in scope, why did you pick 9? And is it ever worth going to some FFT or NTT-based multiplication strategy over Karatsuba? Or because of the fixed size due to the stack limits, Karatsuba's always best? Or what are the trade-offs there?
Yeah, we did base cases, hard-coded base cases up to size 9, basically, because at that point we run out of registers.
Great answer.
If we had more registers, we could do bigger base cases.
Oh.
Okay,
sorry.
So yeah.
Please.
So for entities, actually in the slide I showed for high multiplication. So this slide only goes up to 60 words, but our high multiplication routines works for arbitrary large numbers, and it switches to NTT actually at very high precision. But this is for much larger numbers, and it's an interesting problem to make entities efficient at as low precision as possible, because there are nice things you can do, like when you pre-compute the transforms for operands that you reuse, and so on.
I see that Andrew has a question down here. So maybe we'll hear, Andrew, if you want to.
Well, I think I was last in the list, but it was just an obvious question, which is, what are your options for GPUization?
Yeah, so this is something that I plan to look at with Albin Albeck, actually in the future. So one of our projects will be to look at compiling straight line programs to run on GPUs, where we will consider this kind of representation. And well, for things like matrix multiplication, I think it makes most sense to switch to RNS multiplication for very big matrices. But for, let's say, small operations, small vectors, where you maybe consider operations on many vectors, many short vectors, it's straight line programs might be interesting also, compiling straight line programs.
Maybe one last quick question from Pavvel before we switch over.
Sure. Yeah. You pointed out that it's pretty close to double-double performance. What's the additional overhead that you're doing that double-double isn't? Is it like exponent handling? Is it something else?
Yeah, it's exponent handling, and then so I should mention, so the double code I'm testing here, it's just a naive C implementation of double, and I let GCC auto vectorize it, and probably you can get better performance if you hand code for SIMD. So it's more or less comparing serial code, I would say. But anyway, yeah. The advantage of what we're doing is that the serial efficiency is really good, because basically you get the CPU can compute a 128-bit product in a single cycle and interleave that with the additions when you do things very carefully. While with floating point expansions, on one hand you have very wide vector units these days, but also you need to do several operations to get the same precision.
Mm-hmm. Yeah,
but
very
yeah,
cool work.
it's mostly a question of overhead at low precision.
Super cool work. I think with that, thanks again, Fredrik. We're gonna move on to the next speaker. Amir, if you want to set up, let's see if the screen share is all working. Beautiful. So Amir's here from Queen's University Belfast, and going to tell us about software-defined floating point number formats. So Amir, please take it away.
Okay. Thank you so much. Okay. Can you see my slides?
They're up.
Yes.
Okay, that's good. So, hello everybody. My presentation is about software-defined floating point number format, which is based on our recent paper in IEEE. First, a few slides on motivation. So, if you read some papers in the last decade on measuring the energy consumption of the data transfer between memory and processor, and also the energy consumption of the floating point addition or multiplication, you can find that the data communication requires significantly higher latency and energy consumption than floating point addition or multiplication. So actually computing is bottlenecked by the communication. So from this point of view, in our project, we concentrated on off-the-shelf standard processors. So in a standard processors, we have only two options, single precision and double precision, for represent real numbers. And for a lot of scientific applications and iterative applications, such as graph processing and other applications, we need to read and write a lot of floating point data to the main memory during program runtime. But do we always need single and double precision for all applications? So if not, can we use a smaller format, and how to implement it on the software, for software? Because I know in server line processors, recently we have bfloat support. In interprocessor or in GPUs, we have also support for low precision. But in a standard processor, how to implement such kind of low precision customized format? So the goal of our work is first, fully application specific. We used specific features of the application in order to optimize and reduce the format size as much as possible, in order to reduce the cost of data communication between different memory levels. Also, our aim was to entirely achieve a software implementation without the need for FPGA or any change on the hardware side, and also any change in the compiler side. I will describe more. The other thing, ensure correctness. We performed complete mathematical investigation and proofs to ensure that this particular format for this particular application can generate meaningful outcome. And so the our aim was to design a memory format in order and use the hardware supported format single per second to perform the computation. So convergence are needed between our software defined number formats and the single per second. So efficient in convergence is a key part of our contribution. So about the application, for this specific paper, we selected belief propagation just as an application in order to show how we can design and develop software-defined number format. Why BP? Because BP is a data-intensive, iterative application. And also BP for loopy graphs is inherently approximate. So it can tolerate low precision floating point data types. It is a message passing algorithm, and we have some nodes, and each node generates messages and propagates messages to the neighbors. So we completely investigate the formulas behind the sum product belief propagation, and just for one of the data arrays, the normalized message arrays, we applied our technique. In other words, for any other required variables such as H factor, node factor, we use single precision just to prevent the even a small overhead of the data convergence. Only for the critical array that needs to read and write during each iteration, we use our format. So first, we investigated the formulas of the belief propagation, and we proved that belief propagation for Ising grid data sets, for difficulty factors of the C equals 2 and 3, the range of exponents will be limited in a small range of -5 to -1. This means that only 3 bits are enough for exponent. So 8 bits in single precision or 11 bits in the double precision are more than enough to represent normalized messages in belief propagation. For details about the proofs and the mathematical details, please refer to the paper. In frames of the 16 and 8 bits, we selected different sizes for the exponent 2, 3, and 4, just to see the effect of the 1 bit more or less in the exponential matrix on the accuracy and performance. And we developed 5 formats, but our main 4 formats is the mini 2 and 6 as an 8-bit format with 2-bit exponent and only 6 bits mantissa. So, conversion mechanism. In our format, we develop extremely simple conversion mechanism in order to prevent overhead of the conversion. You can see that for conversion from the single precision to our purpose half precision format, we used rounding towards 0 in order to minimize the cost of the rounding, a simple truncation. And we also ignore the sign bit because normalized messages in BP are unsigned probabilities. So we don't need sign bit, and we can use the sign bit in order to increase the precision. You can see that the forward converter is so simple, and the reverse conversion from the half per second to the single per second only requires adding some 0 bits to the LSBs of the mantissa and 0, 1, 1, 1 to the MSB of the exponent. For our mini format, everything is similar to our half per second format, rounding towards 0, truncation, only for the exponent conversion, an if else was required in order to change the exponent, but in order to increase the efficiency of pipeline, we substituted this if else in software implementation with add and subtract operation in order to reduce the cost of the overhead. And also inside the main residual belief propagation algorithm, we use encode functions in order to translate the single per second to our 16 or 18 formats whenever we need to store the normalized messages. And before every computation, you can see here, before this subtraction or multiplication, we use the decode function in order to convert our memory formats, customer 16-bit or 8-bit formats to the single per second. So we use single per second for required operations and accuracy analysis. So, as I said, belief propagation for loopy graphs is inherently approximate. So even using double precision variables cannot generate exact results. Due to this, we use variable elimination, another algorithm that can generate complete exact results. But this algorithm is so time consuming, so can be only implemented for a small Ising grids. Anyway, we compare the accuracy of different formats, double, single, or proposed half or mini formats based on these exact results and calculate the mean square errors. You can see that the optimum convergence threshold of a convergence threshold is 0.1, and for this convergence threshold, our half per second formats and even our mini format can achieve the same accuracy as the even double or single precision. Because actually double and single precision is more than enough for this application, because we have high algorithmic error inside belief propagation for loopy graphs. And for the performance evaluation, first, all the previous software libraries for the belief propagation were based on the double precision. So our proposed approach, you can see that half or mini precision, for the largest Ising grid size, we achieve up to 70% speed up. And we also developed a fully single precision version of the library and compared the runtime. Based on it, you can see that our mini format achieved up to 40% of speed up. Fine. So we propose software-defined number formats, an application-specific, fully application-specific format in order to reduce the cost of the data communication between memory and processor. When we fully implement our approach in software, we just add a few lines of the code to the existing libraries of the belief propagation without using FPGAs or any customized hardware, and or without changing the compiler, and our formats achieved up to 70 and 40% improvement. without sacrificing accuracy. In other words, our aim was not designing any approximate format. We just tried to identify the required precision for this particular application, for this particular data set, and then just store the right amount of the data in the memory. Okay. Thank you, everybody.
Thank you, Amir.
Okay.
There's a couple questions in the chat. Maybe to start them off. One thing I was curious about, in your actual implementation, are you just doing sort of table lookup for the 8-bit formats?
No. It is possible to do that because we only have 2 bits in the exponent. But no, we converted the 8-bit formats to the single precision and performed operations, computations with single precision, with flutes.
I see. Ganesh also had another question, and Andrew as well. Let's go with Ganesh.
A quick observation. I read that EFI-M2 is supported in Hopper. You're kind of close to it. Your E6, no, EFI-M, what's it? Your E2M6, your yeah.
2.6,
Yeah.
yes, E2M6, yes.
Yeah, so maybe you can climb to the closest hardware and see what you might lose, like E4M3 in Hopper or something like that. I don't know, yeah, whether that makes sense, because then you have native hardware, assuming you can allocate a Hopper. Yeah.
Okay, yeah, yes, we just use this E2M6. Another point to add is that we think for every application, we have opportunity to optimize the data. Okay, due to this, for this particular application and data set, maybe 2 bits are enough for the exponent. And for another application, maybe another. So due to this, we were not going to find a generalized approach or try to use the existing formats. But yes, in a case of we can also consider using the existing formats, and even bfloat formats, the existing news processors can be reused in also perform computations in addition to the only memories.
Okay, and I think Andrew, Andrew also has a question, and then I think we'll go to break.
Yeah, no, it feels like some of these results might extend to graph neural networks as well, which people use for, molecular machine learning and some other applications. It might be interesting if that applies.
Oh, okay. Thank you for suggestion. We'll check. Okay.
Fantastic. Okay, Amir, thanks again. I think that now we're going to go to sort of a 30-minute break. And let me just share the slide for the next session, so to whet folks' appetite. But yeah, we'll leave the Zoom up. But this is a good opportunity for people to grab another coffee, or if you're in the Seattle area, we've got about 15 donuts left here in the room, so people are welcome to that. But yeah, we'll come back here in about 30 minutes or so. If the speakers could come back about 5 minutes early just to double check everything, that would be fantastic. And thanks everybody, and we will see you soon. Okay, folks, I think we're going to get started here in about 5 minutes. Just a heads up. And people should feel free, by the way, during these breaks to unmute and chit chat as part of the broader water cooler vibe of the FPTalks mission. One thing we were just talking about here on this end, one of our friends in the running club has been working on analyzing some video time codes. Is this still shared? Yeah. And it turns out they had this very funny error in converting between, there's a standard for timecode format in video, and going between that and actual timestamp is a little bit more subtle than you might expect because naive implementations don't round correctly. And so they've been going through this whole thread now trying to figure out the right decimal format, or should they go to higher precision or what? I just thought it was kind of a great example of how, even in 2025, just doing a simple scaling is quite fraught. There's a lot of software out there that still struggles around this stuff. So if folks have ideas on how to help on this, if you look at the standard, it just says use sufficient precision to ensure there are no errors, without any indication of what that precision might in fact be, or how to tell if you have enough.
This is a great example of someone once doing a clever hack, sticking a metadata frame every 1,000 video frames just in line, and is now, like, many decades later, causing real trouble.
Yeah.
Maybe we can change the word 1,000 to 1024.
Yeah, right. If they'd stuck a metadata frame after every 1023 frames, it would be so much easier.
Shall I share just in case?
Yes, please go for it. And I can stop this one.
Can see that.
Beautiful.
Okay. And let me just see if I can get the chat up at the same time. Okay, so I assume my Zoom is not including the slides.
No, yeah. It overlays it, but only on your end.
Yeah. And can you see my mouse if it's here? Sorry, over the P3109.
Yes.
Yeah, fine. Okay, so that goes through. Yeah. See myself, which is pointless.
Okay, well, I think that we will go ahead and start warming up for the next session to start here in about 15 seconds. We have a real treat especial, and in some ways a direct response to the challenge Jean-Michel kicked us off with in the previous session, which is Andrew Fitzgibbon here from GraphCore and the IEEE working group on formats for arithmetic for AI workloads, to tell us about what's going on there, what folks want, how we're going to get specifications that support building hardware, reasoning about these things, and making the world sort of understandable and things be able to interoperate. So really excited for this. Andrew, please go ahead and take it away.
Thank you very much. Absolutely great to be here. And yeah, hi, Samir Agrawal. Great to see you. Yeah, so I'm not a floating point person. I'm kind of an AI person, but I've ended up learning quite a bit about floating point. So I was just going to take us through. I'm sure you all know lots about AI, but I'm going to do it kind of from scratch anyway, using the lens that I use for most AI, which is not the picture on the left, which you normally see, which is some picture of image and then boxes and arrows. This is like, if you want to program in Scratch, then maybe this is a good way to represent your models. But I prefer to represent an AI model, as a sequence of code statements. So what is this AI model that I've drawn on the right here? Well, it's a function that takes in some data structure, which we can see here as a tuple of tuples by reading our Python, which we'll call the weights, and another data structure, which might be an image flattened into a 768, into an n vector, or a batch of images, which would be an n by b matrix or whatever the inputs are. And what does the AI model do? People call them activations. They basically, do some matrix multiplies. This is the Python symbol for matrix multiply. So some of the weights matmul some of the images, and some values are added. They are passed through the nonlinear function. This one's called ReLU. Others are used. And, you do that kind of again and again. I think and then the output is a vector of things which we call probabilities, i.e. if you're classifying digits, each image in your batch will get 10 so-called logits. And, the highest one is the one that your image is supposed to be. Interesting to see that, sort of transcendental like exp and, arctan and hyperbolic tan are relatively common in these codes. So that's a very simple two-layer model. Deep machine learning is, your weights data structure is now a list. And we repeatedly, we run through our list and repeatedly apply nonlinearity and then linear operation and pass them through softmax. So a layer is just, one of the parameters called in this loop. That model is not as interesting as this economically interesting model, the so-called transformer, where we crank all the numbers up a bit. So typical vector sizes are maybe 32 kilobytes. Maybe the dimension is 16 kilobytes. Maybe I have a 4,000 by 16,000, sorry, 4 times 16 by 16 matrix. So huge matrices. Interesting things, I think, are that we still have kind of minus infinities are used in the code. You could argue whether or not this is a good idea, but we've got floating point. Why not use it? So this is a practice where people want to make the transformer look only at values in the past. So I'm going to make a lower triangular matrix of the size length of sequence, and log it. So I get minus infinity below the above the diagonal and 0 below the diagonal. And then that lower triangular matrix is used, it's added to some value. So what we've got here on the right is basically, on this slide, is basically all the code for a transformer. What happens, symbols come in, they get looked up in an embedding matrix, they are repeatedly divided by something, linear thing happens, more matmul happens, and then the thing you'll know about called attention, where for each token in the sequence, I dot product the current activation vectors, and magically that adds them up in such a way as to simulate intelligent conversation, and more matmuls. So that's great. So that's your, there's your introduction to AI. In fact, that's all of AI pretty much. No, it's not, because that was just inference. So what does training mean? Training means I take my AI model, I write a function to classify, which is, take the argmax of the 10 values that would have been output for this image. And of course, ideally, I would like to say for my set of 1 million image label pairs, I would like to find the W's which make the smallest number of mistakes. That's not a differentiable function. So instead, we look at these so-called probabilities and say the right answer should have had high probability. And that's the algorithm. I'm showing you all of this just to kind of emphasize the amount of exponentiation that seems to go on everywhere. And then, of course, very quick mental model. So here's my forward model. Here's the gradient code. So of course I need to compute the gradient of this model, so I can just write it down here in code. And roughly speaking, every matmul in the forward pass gives you 2 matmuls in the backward pass. So you can think of kind of 3 times the flops to do the training than it would be for the inference. The other thing that happens in training is a lot of memory pressure, because the activations like this Y1 here is kept until, or let's say T1 is kept until the end of the backward pass. So there's a sort of massive increase in memory requirements when you have to remember values for the gradient that you wouldn't have had in the forward model. So that's, again, it just means peak memory transfers, yeah, it's all important. And the cluster, the problems are kind of the same whether you're running on a phone or on, a rack of 1,000 machines. It's flops and memory bandwidth. And again, dynamic range. So if you simply write what I showed you here, my simple FFN, and you initialize your weights from a uniform distribution with standard deviation 1, you'll get an inf in the output. So, 101, you're going to have questions of numerical stability, even with sometimes careful implementations. Okay, so in AI, large matmuls, operations like max and relu, we need floating point. The gradients are going to be small, so we're going to need floating point values to represent them. And then the trend that we've been observing, of course, is that you can get away with smaller formats. So 32, 16, 8, 6, 4. And when you use smaller formats, things go faster, they're cheaper, you use less electricity, all good. The formats that are in use today, well, these are just the OCP, the Open Compute Platform formats, a variety that we all know about. And of course, as you might see, they have sort of a variety of characteristics in terms of, do they have nans, do they have infinities, precision bits, and so on. That isn't the only format out there, although it's by far the dominant one. There are other formats like formats from my company, GraphCore, formats from Tesla, and this is a sort of a little cross-check table of characteristics of the formats. Do they have exactly one nan? Do they do subnormals? Do they have infinities? Do they have -0? What the bias is? And the point here is that there's no format that agrees with everybody. So of course, what are we going to do? We're going to add one more format that is different from these, and not just one more. So P3109 was formed with this request that we do a consistent and flexible format. Consistent obviously kind of means we can't use this OCP format because they're not consistent, so therefore they're not flexible. So that's fine. Why does I'll get to that. Yeah. I kind of cut to the answer, right? So we need fast small floats. Here is a 6-bit float format that you would get if you followed IEEE 754. Right, you'd have nearly 10% of your code space would be spent encoding nans. You'd have a -0 up here, which we don't really have a use for in AI, or at least I haven't found one. And here's what you could do with a slightly different formula. Format. So this is the P3109 recipe. There's a single nan at the -0 point. There are positive and negative infinities, although we've just made those optional. So I'll talk about that a little bit. Not optional, I mean doubling the number of formats. We have subnormals, as Zachary says. Again, a lot of AI has gradients, and gradients might be small. So good, more values near 0 is a good thing. The exponent bias we've used here, we've chosen to make the same, so we get the same Emax as 754. So Emax, as we can see here, is 3, and Emin is -3, so it's symmetric there. And that gives us a funny property that the 1.0 is in the center of the range. So in this 6-bit format, OX10 is 1.0. In an 8-bit format, OX40 is 1.0, which is kind of fun. And this is just the positive values. Sorry, you guys are in the way. Yes, it's positive and negative. Yeah, okay, so that's the recipe. Binary K, PP, delta sigma. So that's width, smaller than 16 bits. Precision can be from 1 up to K-1. The domain is finite or extended, which means are the infinities present? Are we in the extended reals or are we in the finite reals? And then we put in assigned and unsigned formats because existing practice includes those, so they're noticed. Now, you will immediately notice the bottom of the slide. That I'll do the math for you. There are 224 formats even before we multiply by 2 for adding and subtracting infinities, right? No one is expecting any vendor to support or to accelerate all 200 or 448 defined formats. Sorry, funny joke that 224 is max float for binary AP4, so that must be the correct value for the number of formats. No one's going to support that, but what we're doing here is giving people definitions that they can use in order to say, I implement P3109 binary 7 P3 S, U F. So it's just it's a set of definitions. So whereas sometimes we think in standardization that our job is to restrict people and say you can't do, I say first define what you can't do, and then tell people what they can and can't do. And of course people will always do subsets of these things. Right, just very quickly, the standard or the document already contains quite a sort of formal definition of each operation. So an add scaled operation, which takes 2 log, essentially exponent biases that applies to the arguments, is described formally as decode input 1, decode input 2, perform math in the extended reals, and we define the extended reals, and then project into the output space. There's lots and lots of detail. I'll cut to the goodness in a minute. So what is a projection specification? A projection specification says what your rounding mode is, and we will add stochastic at some point, or some stochastic modes, and saturation. So somebody was asking about that. So each operation, in principle, and already NVIDIA does this, people do this, the opcode contains the rounding mode and the saturation mode, right? So you can either clamp preserving infinities, so infinities that come in stay as infinities, or just overflow, so replace with the extreme value. That's the projection mode. That goes into the project function, which is simple: round, saturate, and code. Round is, some sequence of math that's supposed to define rounding. And at this stage, you should definitely be thinking, is this correct? Sorry, there's saturation. Well, we wondered too if it's correct, so we obviously wrote code implementations. And then just recently, if you're at a RITH, Christoph Wintersteiger took our definitions, converted them into an OCaml-like specification, and pushed it through their theorem prover. So we can now prove theorems like, every integer between 0 and 2 to the k decodes to a float, that we have correctly added all the special cases for nan and inf, because if we hadn't, this theorem would fail because we would have, for example, added -inf to inf in the extended reals. So that's the kind of the big new news, I think, is that, we've got a decent set of theorems about these that lead us to suspect that the definitions are correct. So there we are. Current status is a family of floating point formats with precisely defined operations semantics. And yes, we'll work on things like block formats, stochastic rounding, possibly round to odd. We've had a quick look at putting that in. It looks not that hard. Right. Sorry, I'm a bit over time. Thank you.
No, this is super, super exciting. Thank you so much. It was great to get this update. Pavvel, do you want to go first on questions?
Yeah, sure. Happy to do so. So one thing you mentioned was how important these wide exponent ranges are for applications in machine learning. And I just wanted to know, like, how essential a property is that? Do you really need numbers across a wide range of exponents, or is it just that you need like the largest exponent, or you need like small numbers and big numbers for different use cases? If you had like scaling parameters that you can put in the floating point context, or if you had, some kind of scale addition operation, could you get rid of a lot of the need for large exponent ranges?
Yeah, so yeah, good to look at the scaled addition operation. Yeah, it absolutely is the case that, so how does machine learning work? People do experiments, right? They train with E5M2 and it doesn't work, and they train with E4M3 and it doesn't work. And eventually they come up with recipes like you need, and I'm going to get this wrong, but you need one of them in the forward pass and the other in the backward pass. So in one case you need wide range, in the other case you need high precision. So it definitely happens that a single computation will use, or a single, training run will use more than one of these formats. It's absolutely common, as you say, to provide these scaled operations. So this is a, in one atomic compute x scaled by 2 to the power something plus y scaled by 2 to the power something. So even though we have those, we still need the variety of formats. Now, do we need exponent 6? Yes, E8M0 is a pure exponential format that people use for essentially like these power of 2 scaling factors. Do we need E2? I don't know, but it wasn't a problem to define it. So let's define it and people can figure it out. Yeah. To this point, did somebody said Mantas said accuracy? Yeah. So the only thing we define is the correct rounding under, the rounding under these set of rounding modes that we've defined, right? So this is, we essentially only define, I guess, correct rounding. There's a sentence in the report that says, if you have a system, you may declare it to be a number of ULPs away from the specified answer, but it's just sort of one throwaway sentence. It says you are allowed to say, I do P3109 addition with a 4 ULP max error. But yeah.
This is fantastic. There's actually a few more questions also still in the thread, but I think we're gonna go ahead and jump to Sam. If folks in the break want to hang out, I think that there's a lot more discussion to have here. This is super exciting stuff. Thank you so much, Andrew.
Yeah, you're very welcome. Thank you.
Okay, up next, yet another treat especial. Sam Coward is going to tell us about a data path dialect for representing ops with carry save results. And it looks like this is an anti-egraph screed based off of the top right corner. So I am very curious, Sam, to see what you have to say for yourself. With that, please take it away.
Hi, thanks everyone. Hopefully everyone can hear me everything. This is going to be way more hardware-y than all previous talks, and I will preface that there are going to be no egraphs. Usually can be found talking about egraphs, not for today. This is very much a work in progress and has been largely done during my time up in Cambridge. And so if we take something silly, which everyone in the AI world has just been talking about, trying to do a dot product, but turn it into a 4-bit integer dot product, and we want to make a circuit out of this, what would it actually look like to go and implement this as a circuit? Well, we'd start off by constructing some partial products. Namely, this is like, go back to your school book arithmetic, take the first digit of C, multiply it by D, second digit of C, multiply it by D, so on and so forth. And then we do something weird in the kind of hardware design world. We actually reduce these down into this carry save representation, where we can think of this as producing 2 outputs that when you add them up, using what we call a carry propagate adder, this gives you the correct result of the multiplication. And why did I talk about redundant numbers representations? Well, this is because, say you wanted to produce 3, you can produce 3 as 3 plus 0, 1 plus 2, 2 plus 1. There are many choices, and this compressor tree doesn't necessarily specify, it sort of parallelizes your reduction, but doesn't actually compute the full carry propagation. And carry propagation is really expensive. It's going to scale with the kind of bit width. So it's something we really want to avoid in circuit design, or in digital circuit design at least, more generally. So obviously A times B looks pretty similar, and then we've got another addition. And what we can notice here that if we got a couple of additions going on in parallel, basically we're doing carry propagation twice in a row, and really an efficient implementation of this thing, which is super well known. This is nothing revolutionary. It's been done, many years ago, is to try and reduce this and put this into a single compressor tree. So feed in all 8 inputs, all these A0 times B, C0 times D, all into this and add them up all in parallel, basically. And we can do that by reducing it down to 2 things. And, in the 4-bit case, this is not really that wonderful, but in the 16-bit case, it does start to look a little bit more interesting, quite a lot bit faster, just because you've removed that carry propagation from your critical path and you've replaced it with this parallel thing. So what does that mean in terms of when we're building sort of compiler-like tools or EDA synthesis tools, is that your intermediate representation should really express these efficient circuit constructs rather than just focusing on like multiplication and addition or like even bigger things than that. And so that's kind of the inspiration behind trying to do this data path dialect. It's certainly maybe buried within commercial tools, but we cannot see the IRs of these things. Many of these techniques are well known, but I certainly haven't found it in sort of open sourcey domain. So that's part of the idea here. And we'll come on to why it's a bit weird as well later on. So obviously we did this in MLAR, and we can represent this bit of blob of code, which looks a bit weird, but you basically can define a partial product operator that is taking in 2 inputs, A and B, and they have this integer 8 types. This is just an 8-bit result, and they produce 4 results. And you can see how they correspond to our partial product that we had on the right. We can do the same for C, and we can define our compress operator. None of this is looking too weird, other than we can just see exactly what our compressor is doing. And this actually exposes this within your intermediate representation itself. And then we can finally sum up the carry and save in this final output to get the desired result, all hunky-dory. What is weird is that we don't actually specify what sort of AB0 is going to be. There is no, actual concrete, this is the specific value. Going back to that, we can represent 3 as 3 plus 0, 1 plus 2, 2 plus 1. There are many choices about how you can do this. And so this is what causes a lot of like worries and concerns in hardware companies and chip companies when you're trying to use these techniques, is how do you actually go and you can simulate them and verify them, because our solution to that is to try and verify them via these contracts. Namely, we don't specify precisely what AB0 and up to ABN-1 are going to be. We only specify that when you add up these things, namely we add up all the results on the left-hand side, it's equivalent to multiplying the results on the right-hand side. We can similarly do this for our compress. So in this case, we've got our compressor that produces 2 results. And when we add up those 2 results, we can assert that that is equivalent to adding up all these 0 up to n-1. When you discuss this with kind of software people, I think the analogy is say you've got some undef or like sort of poison values running around in LLVM. You can specify that something is an integer, but not give it a value. So you know something about it, right? You know some properties about this value, but you don't actually necessarily know that it's 0 or 1. You just know that it's an integer type, for example. So I think that's where the common ground is with the software folks. And why do we actually want to do this? Well, it allows us to now go and implement some, I think, interesting optimizations that it's difficult to do. It's difficult to express in Verilog or something like that without having to resort to nasty gate level code that's hard to verify and actually consumes a bunch of time. So if we were to add up A and B, C and D in the first pipeline stage, and then register them and pass that on to the second pipeline stage and add them up again, that's not super efficient, because what we can do is we can actually replace this by a compressor tree, which still uses the same number of registers and stores this in our carry save, and then add up these things on the output. We can also do some other things, which is one of the optimizations that one of the logic synthesis people at Synopsys talked about many years ago, about kind of unsharing, which we would never really often think about unsharing. But if we want to go faster, this multiply A times B might get split up into a partial product compressor tree. And again, we've now got our 2 sequential adds going on. And so we can save, so if we're trying to produce A times B plus C and A times B plus D, well, we can actually save a bit of critical path delay by replacing those adds with compressor trees at the expense of some additional area, but maybe that's going to be worthwhile in your particular design. This also allows us to do a lot more optimizations, and we can verify them, each of these steps by using those SMT contracts. So that SMT encoding that I talked about just a minute ago, where we can actually take our data path operators and reduce them down to SMT. So what we can do is we can do optimizations for A plus B times C, A times B times C, and actually, propagate these carry save values over other logical operators, being very careful about how we're going to actually manipulate some of these things, as this is a great way to introduce bugs. If you go and talk to the logic synthesis companies themselves, they will say that this is where they are absolutely petrified, and they will get things. I don't know if they get things wrong, but they certainly are very cautious about how they manipulate these values, because they need to be sort of stored together, because they only have this property. You don't necessarily know what they're going to be. And this is really because you want to defer the implementation until you have some more timing information. That's one of the real critical reasons to do this. So yeah, in conclusion, if you want to go take a look, this is all in this MLIR circuit project, which is an open source project. We're gently upstreaming stuff, so you can go and have a look at it. We've also put together a bit of a data path design benchmarks, but would love to have people, particularly from hardware companies, sharing their different designs, things that they would care about, so that we can build up a bit of this data path benchmark to rival something like the logic synthesis community has. And we also need solver improvements. This is kind of surprising, but if we take Bitwoozler, which is the leading SMT solver, and we go from 4 to 12 bits on just like simple optimizations that I've done using these things. This is when I've actually concretized this into a real gate level implementation. We kind of blow up at about 12. This is getting into several hours of runtime, even at just 12 bits. So something that the closed source tools do a lot better at than our open source tools. So for sure, it'll be interesting to see this pushed. But yeah, thank you very much.
Thank you so much, Sam. This was fantastic. It looks like we have a question from a true architect here. Adrian, if you want to kick things off.
Oh, sure. Hi, Sam. You actually just kind of half answered this at the end, but I was just curious, like you were saying, like, great, we can do a lot better if we sort of relax the condition on the, wait, am I audible?
Yes, you sound great.
Okay, awesome, good. Like if we relax the condition on sort of on the different pieces and don't say you have to reduce these values, but they sort of
Sam
have to
can't
sum to
hear
the right
you.
thing.
Sorry, Adrian.
Really?
Sam can't hear you. We can hear you, but Sam cannot.
Okay.
Sam, are you?
Let's give Sam a moment.
Okay, everybody grab a piece of paper. You can write your questions and hold them up to the camera, and Sam will be able to read them.
I think Sam's gone even further now.
Indeed.
I wonder if he's just rejoining.
Yeah.
It was a great talk. We can all just bask
in the glory.
Yeah.
Also, I love the challenge problem of like make reasoning about multiplies fast in SAT, which is one of the like oldest grand challenges in SAT forever. I feel like Sam, you're setting the bar too low for us.
Apologies. That was a sound disaster.
Oh, no problem. I was just hoping to get your thoughts on like whether you're making like is the verification problem now fundamentally harder now that the contracts are more permissive? Does this make sense? That is like that now that there are data pairs flowing around?
Yeah, to an extent, like I'm certainly building bigger things.
Right.
So, you're going beyond just building multipliers. So now you're like gobbling all of these other things into it. So like you might gobble multiple multipliers together. You might gobble like pushing this over logic and stuff like that. So it's the point at which you choose to like separate, when you separate from like having these high level contracts into the gate level implementation. That's the really expensive step. When you're just verifying these contracts, that's really far. And that's part of the idea. Like if we can reason about it at these higher levels of abstraction, then we can prove these things are safe to do, right? Pretty quickly. But then as you go lower, it's disaster. In terms of submitting them to SMT lib, yes, we are working on it as a building up the right set of problems as well, though. I guess I'm figuring out the SMT community a bit. And Z3, like all things die, basically, because you need some domain-specific knowledge, I think. Like, I don't think it's just a case of SAT's going to get better, or unless someone solves the bit blasting is going to fundamentally change, because like all these bit blasting approaches work on like unrolling your adders, and that doesn't necessarily play very nicely with when you're doing this parallel reduction thing.
So Sam, what if you did some kind of symbolic reasoning about the multiplies, maybe using a data structure that helps propagate equalities?
Yeah, I mean, so I think the best thing in this is what the ACL2 folks have done on how they can do like a term rewriting approach to recognize these larger structures. So yes, but if someone wants to do that in something more friendly than ACL2, that would be wonderful.
Interesting. Okay,
But
thank
I
you
think
so
if you just throw this at egg, right, it's going to blow up, because this is all the e-graphs for logic synthesis papers are all on how do we scale this thing so it doesn't just fall over and die. And people have done loads of efforts in this thing.
This is great, Sam. I suspect there will be more discussion also in break. Let's continue on though. Pierre's gonna join us and there you are. Talk about pushing Math.h improvements out from ARM. The process there, what it looks like. So I think basically a big chunk of people here are using ARM chips as we speak, and I suspect the math you rely on is stuff that Pierre's been looking at working on improving. So let's hear more. Pierre, please take it away.
Thank you. Yeah, so we're going to talk about Math.h. So basically, I'm taking you back to the software world, more specifically the C standard library. And so by Math.h, I mean all these functions and more. And I want to give you a little bit of insight on how we optimize these vector functions and also how we get to upstream them. So first of all, I'm part of the numerics library at ARM. We develop open source numerical libraries for infrastructure and client. And I'm based in Manchester, and I lead a team that works for proprietary as well as open source software. And today I want to focus on ARM optimized routines, but we also have linear algebra libraries. We have computer vision, 5G, random number generators, security libraries, video codecs, all that stuff. So yeah, let's look at what we have in ARM optimized routines. So we see that this is a GitHub repository, open source, and we see it as our vehicle for upstream. So the optimized routine that we come up with, they first land in this project, and then they make their way into the C standard libraries. So the reason we do it is ARM cares about people, users getting performance by default on Linux, Android, or other OSs. And our emphasis is on GNU libc at the moment, and it gets shipped as part of Ubuntu, for instance. But other projects pick up AOR sources directly, and Android is the case for now. In ARM optimized routines, you have AR64 optimized version of Math.h, but as well as string.h, and also recently software emulated floating point arithmetic. In the Math.h, we provide scalar math, so libm basically. It's cross-architecture, and we also provide vector math, which would be libmvec in the GNU libc world. These routines have relaxed accuracy, so don't be scared. They have 4 ULP, but that is because that's what GNU requires at the moment. So we provide 2 interfaces for vector. We have Neon, which is 128-bit on ARM, and that's available by default. We also have the scalable version, SVE, and all the code is written in C using the ARM C language extension, ACLE. So basically, we're working at the intrinsic level. And that's because it's documented and it's easily maintainable. I'm not going to go in the detail of the when, but here's the roadmap of how we provided these routines in scalar and vector form and how they progressively made their way into the glibc. And you can see that, for instance, after working on the optimization, we got to reach parity with x86 in glibc in 2024. And in the meantime, compiler had auto-vectorization features enabled, and GCC, for instance, 2024. And this year, we're working on C23 routines, as well as a project to upstream our routing into the LLVM libc. A bit about the how. So how do we enable this? So it's through a lot of processes, but they are useful for us to efficiently provide these routines and deliver. So for instance, we want people to be able to use the source code and contribute back. So you could ask yourself, why don't we do that straight away in GNU libc? Well, we don't want it to be GNU exclusive for legal reasons. We want to set precedents, especially in terms of licensing. And when it comes to licensing, we're actually very permissive. We started off with an MIT license, so we couldn't get more permissive than this. And by user demand and for the purpose of being usable, the source code being usable in LLVM, we had to patch that and make it a dual license by adding some Apache with LV exceptions. We've got external contribution allowed via signed CLA. This is not great, but because it can discourage contributors, but it's a necessary evil. And what we mean to do by this is also to guarantee code quality. And there's a couple of steps we follow, a couple of processes that allows us to build trust and also make sure we can certify that our functions are ready for upstream. So we've got loads of extensive internal CI for all macro architecture features, and also lots of other architectures for the cross architectures routine. We've got some light public-facing CI through GitHub Actions that is also building trust and making sure external contributions don't break anything. Then comes the big steps. So we've got rounds of technical reviews. So one that's internal before AOR upstreaming, then one that's external before upstreaming into a libc. And this one is actually a bottleneck often because we lack reviewers. We would need the community and people that know how to write these routines to be able to give some feedback and allow these to be merged. We also have IP review that is only ARM internal, but happens at both AOR and libc upstream time. We want to check lots of things, including reproducibility, and check that we don't leak any information, any IP into the public domain that do not need to be. To simplify this heavy processes, we've got simplified, unified GNU and LLVM IP review process. And all these processes make it easy for instance, new starter to go and come and contribute almost in their first month at ARM and deliver some really good code. So I wanted to show you like 3 ways the AOR sources are consumed. For instance, in solid circle, you've got the closed source project. On the left-hand side, AMAS is like a downstream project shipped with AMPL as a binary. It builds and sometimes modifies the sources, but other projects also modify sources. That's the case for Bionic, for instance, to make the code available in Android. It's also closed source, also downstream. It takes a lot of porting effort to get it to the user, but they only pick up the code at release time. On the other end, in the middle, you've got GNU, so the open source project that's our upstream is shipped as part of the OS, and it's a simple drop of the code with very light rework, but extensive technical and IP review. The project for Bionic, for instance, is actually to switch to an LLVM model where we would deliver the code upstream directly, and the code would be shipped with the compiler. The benefit of this is that developers have early access to the latest versions, and also LLVM like to remove dependencies, so that would remove a dependency. There's lots of challenges that come with this that I will mention later. But yeah, enough with all the boring processes. I want to show you a little bit what's under the hood. What is it that we do every day? How we come up with fast, clean, and maintainable vector code. For math routines, we try to improve memory access by using as many immediate instructions as much as possible. we need to have efficient loads of constants. So we use load by pairs allowed by neon. We also try to pack all the constants into one single register and then make use of indexed instructions like multiply and FMAs to speed up the evaluation. And one thing we need to keep an eye on is register pressure for bivariate functions and large polynomial. It often happens that we get stack spills and spurious moves and stuff like this. We want to make sure we've got the appropriate tricks to avoid these to happen and be introduced by the compiler. We're really lucky at ARM to have a few instructions in the ISA that are dedicated to accelerated math. And for instance, the fexby instruction, which is a hardwired table lookup, as well as the ftrig instruction for trigonometric functions, are very useful to rely on to implement fast math. So I want to show you an example on a particularly popular routine, single precision SV exponential. You find it in lots of internal projects as an external in PyTorch, for instance, especially when you have softmax heavy computation like LLMs. So here you can see an AR64 SV specific server optimization, some that I mentioned before, highlighted in yellow. What you see as well is that if you were to look at the ACLE code at the same time, you'd see that there's almost a direct mapping from ACLE to assembly. Because we rely on the compiler, we are still vulnerable to compiler regressions. There's still a little bit of fluff here in grayed out that we wish we didn't have, but we have to have because we rely on the compiler. So yeah, our work is to avoid all these spurious instructions and maintain direct mapping from ACLE to assembly. If you're not used to SV code, so I'll give you a few aspects here that you can see. First of all, this is a vector length agnostic code. It's very it's ease of maintenance for us, as we only need to maintain one function that will run on both Graviton 3, 4, and so on. And you could see that even at a small vector length, like 128 bits, you'd still get gain over neon. Through the use of heavy predication and part of the ISA that's not available to neon but SVE. When it comes to instructions I mentioned before, you see that here we use a fexby instruction. You see that we load a lot of constants into one single register through a particular instruction, and then we use this constant indexed here into an FMLS, another FMLA. And finally, in this fmul, you don't see predication. That's because we made sure the compiler will generate unpredicted function, and that avoids some move prefix. I wanted to show you a bit of performance on a micro benchmark as well as on a macro benchmark to see what sort of uplift you could get from switching from pure libm into the libm vec that's available in GNU libc. So when we measure throughput in nanosecond per lanes, we see that we get like a wide range of uplifts, some small, some very big. Disclaimer is like the fact that some of these numbers are big is due to the reference not being the best possible baseline. It's only showing you an uplift from switching from one implementation to another. The accuracy, for instance, does not match. So this is to take with a pinch of salt. On the left-hand side, on the right-hand side, sorry, you see macro benchmark. So the sort of uplift you would get again, but on a spec benchmark, you see that only very specific spec benchmarks are Math.h heavy, and would get the uplift from the vectorization up to a few percent. Finally, I think I wanted to finish on by telling you about future directions that are going on across ARM. For instance, on the software side, we are looking to enable vector math in LLVM libc, as I said before. And the challenge there is to provide a generic interface first to enable the feature to people in order for them to get correct rounding at potentially the cost of performance. And if needed, they'll have access to architecture-specific optimization as drop-in, and which would provide high performance but with a relaxed accuracy. And the focus here will be on maintainability. Now on the hardware side, I think you'll be interested to learn that we've got a team working on trying to make the accelerated math instructions more broadly available in the microarchitectures, and that is for LLM and softmax, again, application. And finally, we're trying to build a business case to add the augmented arithmetic introduced in a revision of the standard and into the scalar and the SIMD ISA. So that would be key for the performance of correctly rounded vectorized math because it's heavily using double word arithmetic as well as TwoSum through projects. So here we need input from the community to tell us that it's really, really important and absolutely needs to be added to the ISA. And for this and this reason, we're trying our best, but input from the community would be more than welcome. That's it for me today. I'll take questions. Happily.
Thank you so much, Pierre. I think in the interest of sort of trying to get close to schedule, we'll probably just take maybe one question, but then they're all in the thread. So we can also chat during the break here in just 15 minutes. Picking one out, I think Montas kind of just touched on this point you mentioned at the end, which is feedback from the community to be helpful. So Montas, I don't know if you want to ask your question about the contributions.
Yeah, thank you, Pierre. I was going to ask, how can we contribute to the external patch review that you mentioned is a bottleneck for mathematical functions?
So at the moment, the thing that happens is that we tend to have ARM people reviewing our patches and merging them, which doesn't really seem very fair, but it's the only way for us to remove the bottleneck. So I suppose being active in the standard library, which I know is hard, it can be a bit daunting, but yeah, maybe we can set a set of channels so that you actually are made aware that these patches are making their way into the standard libraries, and then you can come and drop some comments. Possibly an easier way is to come and be active on the ARM optimized routines repository, because that's where they learn first. If they get in but you're not happy, you want to patch them, you can raise an issue, and then this will make sure once this issue is solved, the final version will make it into the C standard library. So that's two ways I can see.
This is great. Thank you so much, Pierre. I think we're gonna go ahead and jump to Purva. But yeah, very excited. Thanks for also the community. I'm very impressed that you've been able to sort of wrangle this through management and make the business cases, which is really, really, really nice. Rounding out this session, we have another treat especial. All day we have these fantastic talks. This one by Purva, telling us how to basically efficiently get the answers for probabilistic programming challenges. And it's interesting how this turns out to once again be a really cool arithmetic numeric challenge. So I think with that, we will go ahead and hand it off to Purva.
Thank you. So yes, today I'm going to talk about how this verification approach from this community bit blasting has allowed us to do integer arithmetic efficiently in probabilistic programs. And this is primarily William's work, who was a master's student with me. So yes, let's get started. So the first question is, what are probabilistic programs? So probabilistic programs are programs that represent probability distributions. And I have a toy example on the screen here where we have A and B as two random variables where each of them have a uniform distribution over integers from 0 to 100. And now we are adding A plus B to get C, and now we want to know the resulting distribution of C. Note that we can always sample from these uniform distributions to get some point value of C, but what we try to do in the probabilistic programming community is to get the resulting distribution of C. And this task is known as probabilistic inference. And if people remember their high school math, then computing this distribution would involve calculations, as you can see on the right-hand side of your screen. And these calculations can become complicated as your program becomes more complicated. So to solve these, to do this inference, we built tools known as probabilistic programming languages. And as might be obvious here, that A and B are both integer distributions, and we are doing arithmetic on them. So today I'm going to specifically talk about probabilistic programs with integer distributions and arithmetic. Now this was a toy example, but let me give an example of how integer distributions are everywhere and how there are many real-life applications out there. So in particular, there is this application of loon checksum. So apparently, whenever we get an ID number, very often to identify valid ID numbers from invalid ones, people do this people run this checksum algorithm on their ID cards, on their ID numbers. So let's say you scanned your ID somewhere, there's an OCR system, and what OCR system is going to do, read that ID and give you, and read out the ID number that's there. But since OCR systems are not accurate, they are very accurate, but they are not certain all the time, they are going to give you a distribution over possible ID numbers. Now, if you're trying to check whether it's a valid ID number or not, you need to check that for all possible IDs that the OCR is saying there might be. So in summary, what you have a distribution over possible ID numbers. And what you want to do, you want to check whether whether there's a valid ID number there or not. And how it's done, it's using this loon checksum function, and I have some condensed version of the function here on the screen. And if people see, there is a lot of arithmetic in this function. We have a comparison happening, we have a multiplication, subtraction, addition. So in general, you need to deal with arithmetic and arithmetic over integer distributions. So, but the thing is that in today's probabilistic programming languages, integer distributions have not been well supported. There are these approximate sampling algorithms that would sample one point value for each distribution and totally ignore the structure that arithmetic provides us. And we also have these exact symbolic algorithms that just enumerate all the integers and enumerate the all the possible ID numbers, again, ignoring all the structure. So what we did, we took this approach of bit blasting that was already there in verification community and used it for probabilistic inference over integer distributions. So we said, okay, if X is a random variable over integers, we are going to represent it as a sequence of bits. And now what this sequence of bits gives us is a representation that is amenable to arithmetic. It exposes structure when you're trying to represent distributions, and it exposes the arithmetic structure. So what we do on a very high level is we take probabilistic program over integers, convert it to programs over Booleans, and then convert it to, and then perform inference on it. So first, I'm to demonstrate how this representation exposes structure over distributions, I'll start with the example of a uniform distribution. So let's say you have a uniform distribution on 8 numbers from 0 to 7. We can represent that variable using 3 bits. Now, if we were to go about this naively, we would just flip individual coins and output each number one at a time. We would flip, so this syntax flip 1 by 8 is going to flip a coin with probability 1 by 8. If it turns out head, it would output 0, otherwise it would go to the next flip. If that is true, it would output 1 and keep going. But what this naive enumeration approach is doing for 3 bits for 8 numbers, it's going to use 7 coin flips. And if you have very large integer distributions, which may need 32 bits, you would end up with 4 billion coin flips. This is not what we want. And maybe some people can already observe it, that if you have these bits, you can the probability of each of this bit being true when representing a uniform is flip 0.5. I can say that, okay, with half probability, the first bit is 1 or the first bit is 0. Similarly, once you have decided on the first bit, the second bit can be 0 or 1 with equal probability. And when you represent this bit and you expose this structure, it drastically reduces the number of coin flips. If you had a distribution over 8 numbers, you'll use 3 bits, 3 coin flips. If you have a distribution over 32 bits, you'll use 32 coin flips. Essentially, you go from exponential to linear number of coin flips, making the inference problem much easier. But we don't want to bit blast distributions only. We also want to compute over them. We want to do arithmetic over them. So this binary approach also allows you to do arithmetic, and in favor of that, I would present how we can do comparison. So let's say you have 2 integer distributions and you want to know the probability that y is actually less than x here. So uniform distribution can be represented as the sequence of coin flips, which I described just now. And this comparison function, as one can expect, you start with the first bit, you compare whether they are 1, 0, whether they are equal or not. And depending on that, you either check whether the next series of bits compare or whether you can just return false or true. And when you compile this to a BDD, which we use to do exact inference, you get a small BDD, which is not enumerating all the values x and y can take explicitly. So this really helps in improving the performance of inference. In favor of time, I would skip on addition, but a similar approach for addition also works, where we just encode a typical full adder, and when we present it as a BDD, we get a small BDD, which provides us efficient inference. So we use this approach we implemented our approach in the state-of-the-art discrete probabilistic inference systems, and we found, as we would expect, that with the bit blasting encoding, with the binary encoding, the performance was much better than one-hot encoding. We could scale to 14 bits, which was not possible earlier. And then coming back to the Loon checksum application, where we wanted to see whether a particular distribution over ID numbers, whether the ID is satisfying the validity condition or not. We compared with 3 existing systems, web people, Psi, DP, and Psi, which were enumerating, and web people was taking about 1,000 seconds for like 9-digit IDs, whereas Alia, our bit blasting system, was only taking something about 0.1 seconds, which is a huge improvement. And since it's not exponential, we expect it to scale to much more number of ID digits. So this was like a small snapshot of what we do in the paper, but the paper actually shows a lot more. We show how you can encode categorical distribution using bits, how we can use integer arithmetic for beta Bernoulli models, and a lot more. And we also have this system alia.jl, which implements all this support for integer distributions. It also provides support for continuous distributions. So it would be great if people can try it out and see how they feel about it. Yes. Thank you.
Perfect. Thank you so much, Purva. We got several questions here in the chat. I think so. Sam, maybe you want to ask, although I think maybe Purva kind of got to it. I'm not sure what the timing of the question was about int blasting.
Yeah, I think she got to it, and the independence means that the int blasting maybe doesn't make sense, right? Is that fair?
Sorry, can you repeat that?
Well, like the CVC5 folks, Martin can definitely answer more than me. Like took inspiration from bit blasting and went on to like int blasting, but because you want independence of the bits, right? That
Yes.
basically shows that approach.
Yes, definitely. So so specifically for uniform, we do have this independent structure, and we had like another work which shows that how these bits can be represented independently for exponentials as well. And then we also extended to gamma distributions and a lot more. But for the case of integers, it's mainly there are arbitrary categorical distributions that people want to represent, for which we also have an efficient encoding. It doesn't improve the bounds, but in practice, it's much better.
And then Pavvel also had a question about full adders versus ripple carry.
Yes.
Yeah.
So it
Okay.
is a ripple carry. It is a ripple carry. So we start from the lower bit and then we ripple the carry through. We have looked over like different kind of adders and see if it can improve the performance.
Right. Does carry look ahead make it any faster for solving, basically?
Right. But so for us, the bottleneck is that we represent the final bits as a symbolic formulation. So as long as your logical formula in the end is same, the BDD is not going to change, which is usually the main cost of doing this inference.
So maybe on that line though, like you showed the performance numbers. How much variation do you get under different variable orderings in the BDD?
The variation can be very different. So like if you have, so over here in this BDD, I had like an interleaving variable order where the bits of X and Y were interleaved, and that gives you linear scaling. But if you have all the bits of X first and then all the bits of Y, it's bound to go exponential.
Right. This is super great stuff. Thank you so much, Purva. I think that we are going to actually go ahead and jump to the break. At least on the West Coast, I think people have mostly woken up by now. I know it's getting a little bit late across the Atlantic there. Yeah, people should please, during the break, holler with additional questions for our speakers. And you don't have to be restricted to what speakers talked about. It's definitely totally open. I'm going to go ahead and share as a preview the slides for the next session's schedule, just to get people's appetite whetted. And I think we're going to take a quick break, at least here on the YouTube side, and come back. But people should please feel free to go ahead and jump into more discussion. Okay, we'll come back for officially in like 30 minutes. And until then, please, make use of the space. See y'all soon.
Purva, can you just dump stuff down to a SMT solver?
We can, so we also need probabilities. So an SMT solver with probabilities would work. The easiest way for us so essentially the whole story is that we had a system which already does inference with Booleans. And it compiles it to OBDDs and uses OBDDs for computing this the final probabilities. So what we were looking for, like how it started was like, we want these integer programs to be converted to something that the system can process. But I haven't personally seen any SMT stuff which deals with probabilities as well. So yeah.
And you could do floats as well, right? Did you say that you were already said that.
So we cannot do floats. Actually, we can do fixed points. So because we, in the end, like we need to know how many bits are being used. So we started with like the simplest stuff where we used fixed point representation to have continuous distributions and so on. But I think representing floats would definitely be something that we are looking at.
Yes, the second talk in the next session may well
Yes,
be illuminating there.
definitely.
Ganesh, you had a question for me. Was that sorry?
Yeah,
Was,
be answered by anyone in the group who thinks of frequently occurring ML primitives like softmax, and I have read papers from Facebook, etc., where they talk about 1,000-way or much higher way softmaxes, and you don't need them exact, and you need to clamp them and make them nan-abiding and all that. So it looks like a nice building block ought to have existed by now, where you can gang up softmaxes in a certain arrangement. I don't know whether people have gone that way in supporting these as primitives in ML-oriented hardware, Yeah.
I should know, but I don't.
Yeah. I can paste one or two papers I may have seen from Facebook and so on. It made me wonder. And when I try to look at exceptions that occur in various GPU computational systems, when I examine GPTs running, they don't use the standard softmax. They have softmaxes that have been bent in many ways, So there seems to be a variety there. And it's a frequently occurring primitive. Anyway,
yeah, no, it's obviously it's built on log sum x, but log sum x has this.
Somehow you had to sum it up, and somehow it has to look like a probability distribution, and it has to respect the previous MLP computed inputs values in a way. Yeah. Okay, I'll think about it. Yeah, thanks. But I may post what references I know. Yeah, thanks.
Thank you.
Andrew, did you guys ever look into that when they had the big, what was the Chinese company that blew everyone out of the water?
Oh, DeepSeek.
DeepSeek, yeah. And they had all these like workarounds for dealing with NVIDIA FP8 stuff, right? Does that still apply to P3109 standards, or was that just like NVIDIA's implementation of the accumulator?
Well, it's exactly that. So we at P3109 have not said anything about dot product, because we don't know what we can say. I mean, it's trivial to say, here's a definition of dot product. We do know that NVIDIA, for example, have quite different accumulator precision in the newer in Blackwell over Hopper. Wider. To such an extent, especially with an FP4 dot product, with the 16 FP4s, you can actually do it exact with not much accumulator. I can't remember how much, but it's not very much. It might be 13 bits or something. So again, so you could just do this exact definition of dot product, and then people could say we support that because for FP4 you can. Yeah, the other thing I don't know, but I think it might be true, is I think it's not needed, but you could imagine defining your internal precisions as P3109, 13P7 or something. You could actually talk about the internal accumulators in P3109 terms. I think there might be no value in it. I think you just, implement whatever thing you want.
And if there was a system in which we could then answer questions about it, though, right? Like, how do you answer questions about how big does your accumulator need to be?
Yeah, you simulate. That's what you're getting at, I guess. Or
yeah.
Yeah.
But, like doing that fast and and doing something other than my LLM converged.
Yeah, well, yeah,
Yeah.
it's
A holy
and
grail, right?
even that it's shockingly expensive because, you know, things that you learn on a 1 billion model may not transfer at all to a 400 billion model, and even a 1 billion model is expensive. I mean, it's in the tens of pounds, I guess, to train. The other thing is you might not learn anything in the first 100,000 iterations. So you might not learn anything in a 24-hour run. You might need a 1 week run to learn something, or So that's the other reason for P3109 just being as broad as possible, because stuff will change.
I think Fredrik might have left, but I had a question about some of the infloat work, in particular with relation to potentially doing intervals. Fredrik had replied earlier and mentioned that they're very interested in looking at ball arithmetic. But as I recall, and I think Pavvel will correct me if I get this wrong, one of the challenges with doing balls for intervals is that your endpoints then end up with the same exponent, which can make them not very useful if one endpoint needs, sort of very small and the other very large.
Yeah, I think, is Fredrik here?
I just checked the participants. I think maybe he's, I don't know, it's later there, so maybe he had to go or maybe he stepped out during the break.
Okay.
I'm not sure.
Yeah, I checked their website for the nfloat library, and the website says that the directed rounding modes aren't supported yet. But
I see.
I would be very excited, like, if directed rounding was there. I think, like, the characteristics of nfloat are it's like very fast, assuming you have a static width that you're interested in, and you don't care too much about accuracy. 1 or 2 ops is fine. And like that plus directed rounding is perfect for interval arithmetic, the kind that we do in Rival. And nfloat looks really fast. So it would be very cool to try it out if Fredrik can ever get directed rounding added.
Talk for next year.
Yeah. Yeah, I mean, we're just always working on making Rival faster.
Also, I'm not sure if Pierre is still there or has stepped away during the break, but I would be. Oh, perfect. I would be very curious, like, what is it like internally pushing the business case for all of this open source, like getting this upstreamed? Like, how does that, like, why do people, how do you convince people the value add?
No, it's actually the arm asking me. It's actually management, and yeah.
Oh, they're pulling from you.
Yeah.
Oh, that's fantastic.
But that's the why in my first slide is they just care that people get performance on our machines by default, and that's enough to motivate us to contribute upstream.
Fantastic.
Yeah,
And
Pierre,
and the funny enough, the LLVM project is coming from different angles. It's coming from our own team, LLVM team, needing to remove that dependencies, but it's also coming from Android needing the compiler to be able to pull the new version of the math. So it's interesting at the moment because it feels like people are excited about Math.h again. Wasn't necessarily the case a couple of years ago. And yeah, the pull is coming from a bit everywhere.
Yeah, Pierre, I was a little surprised. I poked a little bit at the sources that are linked from the schedule, and I was a little surprised that you're writing all of this in C, and then in your talk you basically said that you like write it in C and then read the assembly and then mutate the C until you get the assembly you wanted. Like,
yeah.
I mean, you're the guy doing it, so you tell me. But isn't this crazy?
Yeah, it's a bit crazy, but what's also crazy is some vendors dropping assembly code in C standard libraries
Yeah.
and expecting it to be maintained. So we're quite lucky that the compilers are doing quite a good job. And also we're quite lucky to have some people that are good enough at compilers and software that know how to trick compilers. So it's actually quite fun.
That
But
totally resonated with me. I've definitely done that before. Just keep pushing keep pushing compile until the assembly. A trivial way you do it on Intel is just grep for ZMM in the output. Because if you've
yeah,
got ZMMs, then you've got the wide vector things.
okay, yeah, I see what you mean. But to
So
be
you
fair,
don't
like,
even need to be smart, right? You keep hitting the compiler with different options until you see
Yeah,
ZMMs.
but Pierre, I don't even think you guys are using a lot of like SIMD intrinsics. I mean, maybe I was looking at the wrong functions, but I poked around a little bit and it's like it's pretty readable C code. At least in
yeah.
my experience, it's really hard to get readable C code that also is good assembly.
So that's where I maybe I lied a little bit, saying that there's a direct mapping from C to assembly. You still have fluff in C to make the compiler do what you want. So you structure your data the way it needs to be. You put a couple of like compiler barriers and stuff like this. That
Can you pull
it's
up an example?
um,
We can benefit from being on Zoom because you can just screen share.
um, let's look at SVE. Are you okay with SVE?
Sure. You have to
Whatever.
explain what's what, but yeah.
So if you get the data here, it's important that it's const static and all that stuff. You structure the way you're gonna handle the special case. You might have to deal with a couple of like different calling conventions, but here it's fine with SV. Here you've got a pointer barrier to make sure your data is loaded with one single instruction, one address. So that's where maybe there's an assembly trick, but I think this would be portable if it was x86 code. Then after that is basically a CLE, get a bunch of comparison for a special case. You load your constant, for instance. The ACLE will use this load and replicate to load a set of constants that are contiguous in memory here. Oh, and so you've got access to all these constants in one register. And then if you want to do operations using the SVMLA lane, which is the indexed version of the MLA, then you can refer to the constant by using an index, the 0. So here you've got the inf pi to do your shift plus r times inf pi. And you've got loads of them here for the reduction. And then here you see the special instructions for the trigonometric functions. So you've got a special null. And this is like a hard-coded coefficients actually into an MLA. So maybe the harder people will have questions there. Maybe it costs a lot of power, that we want to evaluate that. But in terms of pure throughput, it helps. Doesn't help everywhere. FexPar, for instance, helps everywhere. Where other stuff like this, there isn't that many actually here. But yeah, this is one. We've got other examples.
How do you generate your polynômes?
We've got Solia. We try to make it reproducible. So we've got the Solia files attached in one of the directories.
This is just some like Remez algorithm approximation.
Yes,
Can
yes.
you do
So it's
like
fairly easy
performance
since
tuning?
it's only 3.5 ULP. But yeah, I'm not gonna lie, it is subject to compiler regressions. And so what we try to do is we've got compiler teams, we can feedback any bugs or any regressions that might happen, and then they decide or not if it's something that matters enough that it should be changed. But for instance, one thing you will see from switching to GC14 to 15 is a lot of spurious move instructions are not there anymore. And so we don't have to do anything, we'll just get the gain from that particular version. But it could go another way. The compiler could decide to do the register allocation completely differently, either all at the beginning or all during the execution, and that would change our
Do you
performance.
compare this to some sort of golden assembly, or do you use some lit tests or something to check that it's?
No, I think that would be good if we could do that.
It
We
probably
only
wouldn't be so hard
have,
with
we have a
tuning.
preconceived idea of what good code gen is, and when it looks good, it's good, but it's not always great. You don't know what the runtime is going to do. Or like, so this is definitely flawed, but this is kind of the cost. You know, you've got a cost of being cross-architecture. Like this is the cost of being C, basically.
And I guess, of course, you have regressions that it's actually faster. I mean, you measure the time it takes, so you know if that gets worse.
Yeah. Maybe we need to have a good baseline of what good code gen is, but yeah, I don't think even if sometimes the code gen looks worse, but the performance is better. You know, in ATAN, for instance, you may encounter stack spills, but it would be faster, just because of like how, you know, register are allocated. Just end up being faster, but it's horrible code gen. So this is like there's a trade-off there, deciding what you want.
Yikes.
Yeah, stack spills on like normal CPUs are less expensive than they seem. So.
And again, this is all micro benchmark led, so this is often quite favorable to us. Maybe it's hard to get real life application at dev time.
I had a question. Is that okay? So, Jim Demo, about something you mentioned that you were ARM was considering adding the augmented operations from the last 754 standard. And the way we formulated them was maybe not a good match for hardware because there were 2 inputs and 2 outputs, which a lot of instructions don't like to do. But of course, you don't have to do it that way. You could implement it as 2 instructions, each with 2 inputs. So what are the 2 inputs and the 2 outputs? You're trying to add x plus y, and the outputs are the rounded result and the trailing bit, so the head and the tail of the exact sum. And so you could do that with 2 instructions, but then you'd have to compute the sum twice, perhaps. Or you could have a second instruction with 3 inputs, which are x, y, and the head, so you wouldn't have to compute that again and just subtract it to get the tail. So I'm just sort of wondering, is that an issue in ARM's architecture, the number of arguments?
So I don't know the details of that. I know that on paper, like theoretically, they managed to get an efficient uplift from implementing this. Whether it relies on this sort of fancy tricks, I don't know, and I don't know if I'm allowed to share. But I remember I would trust that they have found a way to formulate it like in an efficient way, and I'll check with them if that's something I can communicate, but I don't want to.
Okay. Yeah, I'd be curious. So thank you.
I will definitely forward.
For something like the TwoSum instructions, I think it fits perfectly for the SIMD instructions, where basically you have 120-bit inputs and then you have 120-bit outputs, and however people want to push these things into the general register is up to them.
Yeah, I'm also very supportive of TwoSum instructions, in floating point debugging, numerical debugging work. Calculating the residuals is super valuable, and I think it's pretty clear that TwoSum or something, some analog of it is like a primitive that you can build a lot of things out of.
So it won't be TwoSum. It will be just the augmented arithmetic, or from what I understand. But yeah, there's efficient ways to do TwoSums with that, and even the fast
Sure.
TwoSum.
You wouldn't actually need to do TwoSum in hardware. You actually could just have a wider set of registers.
Yeah, definitely for error tracking, error assessment would be amazing.
Yeah, the instruction got added because it satisfied 2 goals. One was to make TwoSum faster, and the other one was to make a reproducible summation faster. Yeah.
Yeah, so if anyone can sell that to business team, that's the trick. But yeah, sounds like there's a lot of ask for that, so I'm not too worried. I'm no one really.
Just a quick mention, everybody. We're probably going to start back up here in about 5 minutes. So if you want to get a beverage or another tea or coffee or something, this is a good moment to go grab that. And it looks like all of our speakers for the next session are here in the Zoom. So I think everything is on track. Okay, folks. So ramping up into our third session, last session of the day. Very excited to have Wei Li here from Iowa State telling us about techniques for detecting numerical instability in ML workloads using this technique of soft asserts. Wei, if you want to check your screen share, we can make sure everything comes up smooth and easy here.
Okay, are you able to see my screen right now?
I don't. Oh, not yet. I see double. Oh, there it is. Perfect. Yes. I see it now. And I think everybody else look good. Pavvel, is it coming through? Okay, great. Fantastic. Okay, so yeah, really excited to learn more about this. Wei, please take it away.
Great, thank you. Hello, everyone. My name is Wei from Iowa State University. Today, I'm very happy to share our recent work on detecting numerical instability in machine learning code using a technique we developed called soft assertions. As a motivating example, I'm showing you an MRI image with a clearly visible tumor. However, the model predicts as no tumor with probability of 0.49. And we detected a numerical instability in the training code. Once we correct this problem, the model predicts correctly with probability of 0.81. So when numerical instability occurs, small input changes can lead to large unexpected output differences. So in machine learning, we face a lot of unstable functions, for example, in the PyTorch and TensorFlow libraries. And we require special input to trigger those numerical instabilities. So once those instabilities trigger in the library code, it can propagate in the application code, cause crash, drop of accuracy, and waste the computational resources as models stop learning during the training. So we face several challenges to detect numerical instability in machine learning code. In the past work, mostly we handle NaN and inf. Those are detectable symptoms. However, some numerical instability can cause incorrect values and propagate to the output. As an example, I show reporting low accuracy. Often we require special input to trigger numerical instability. For example, this X and Y vector discovered by our tool, and it can generate output of 0.16, which is deviate from a correct output 0.0896. Such input is hard to discover just by generating random input. And there are a wide list of unstable functions. However, we don't have that domain knowledge to discover which function is unstable. ML functions can be complex. And it's also hard to assert safe conditions. As we know, we handle high-dimensional inputs, and it's hard to decide what's the symbolic checks we should write. And lots of library functions are not documented what are the safe ranges. So our work is aimed to generate inputs to ML function code, ML application code, aimed to trigger those numerical instabilities that can cause consequences. So we designed a technique called soft assertion. It's an assertion placed at dangerous code. In this case, it's unstable functions. And importantly, this assertion is soft in the sense that error conditions are encoded in ML models. In the traditional assertion technique, we write symbolic assertions manually by developers. However, in this setting, consider it's high-dimensional tensors and ML function can be complex. It's very hard to determine what's the conditions that can trigger numerical instability. So our technique is to learn such conditions by running unit tests through those unstable functions. And the output of this assertion is signals that can guide the fuzzers to find such input. So to generate to generate soft assertions, we needed to know what is oracle. So we designed 6 types of oracles using a set of lists. NaN inf is a type of symptom. And there's also a list of range checks As an example, sine cosine function has -1 to 1 range, and some instability can lead to the output to beyond that range, larger than 1, less than -1. So we know numerical instability occurs. There are lots of ML functions can be corrected through math formula rewriting. And also another type of oracle is we can converting some unstable algorithm to a stable algorithm. And we also developed technique to do the cross framework consistency check. For example, we compare output from PyTorch library function with NumPy output library functions. Another technique we use if all the above fails is we increase the width so that we get high precision output. And so once we have an oracle, we can run unit tests to determine when the numerical instability occurs. So how we generate the input for the unit tests, we start with the base input, and we start mutate the input, and then we test both base and mutated input to see if numerical stability occurs in the both cases. So on the top, I show an example. Suppose base input is 10. We do some mutation, we get an input of 30, and we record the output of running the unstable function. We know that 10 is fail and 30 is success. So we log down a training data point that we can use for training the soft assertion. So in this case, we say if the input is 30, we know we need to decrease that input to trigger numerical instability. If the input is 10 and we don't need to change the input, we can trigger numerical instability. So we're collecting a large set of input automatically generated, and those inputs will be used as a training data to train a ML model for each unstable function to encode its error conditions. So once it's generated assertions, we will scan an ML application to see where is unstable functions, and then we were adding soft assertion check. We randomly first generate an input. If soft assertion indicates this input is successfully trigger numerical instability, we stop. If not, our soft assertions output will give guidance. We need to increase or decrease the value in order to trigger this numerical instability. And this will be propagated through an auto-diff component to the input of the ML application code. And this will be used by fathers to continuously search for the input to trigger the bugs. This basically using the assertion can provide more guidance of where is the range we can find the input that can trigger the failures. To evaluate our technique, we're using 79 known bugs and 15 GitHub ML applications. We don't know bugs. And we compared with 5 baselines. And then we reported the number of bugs we find, the time we used to detect those bugs, and also real-world bugs that confirmed by the developers. So our tool, see as SA fuzzer, find all the known bugs in the GRIS benchmark. And we detected 13 real-world bugs, including the tumor we have reported at the first page. So to conclude, this work has a research idea of develop soft assertions, including how to generate it and how to use it with fuzzer to detect numerical instability in ML code. We performed a study to discover the 61 unstable functions and build a database, including implementing 6 types of oracles. And we have an open source tool developed that can take an ML application and report input that can trigger numerical instability. And we compared 5 baselines and find real-world bugs. And one of them has been confirmed by the developers. To learn for the further information, we have paper and tool that you're welcome to check it out and send us questions and comments. Thank you.
Perfect. Thank you so much, Wei. We've got a couple questions here in the chat, and folks, please feel free to add more. Just to kick things off, one thing I was curious about is it seems like this technique is fairly general. I wasn't immediately sure which part is necessarily ML specific. for example, could you imagine also adapting this to large, complex floating point graphics or simulation or other HPC applications?
Yes, that's a great question. I think as a first step, we tried ML applications. It's because this unstable function is tied with ML specific application and libraries. But we can think of the soft assertion technique could be applied to more variety of applications and settings. Even iterative algorithms, we're thinking as next step of explorations.
There was also a question here from Pavvel.
Yeah, I was interested in knowing, so you're kind of using these soft assertions to find parameters that trigger instability, but have you considered just using them at training time to avoid instability? Potentially there are just parameter sets that don't hit the instabilities, and then you don't have this problem.
Do you mean we add assertion in the code, so we just stop the training when or the ML application whenever the assertion is triggered?
Well, the soft assertions are numeric, right? So you could maybe add them to the loss to just guide the program away from bad parameter sets.
That's a great idea. We'll think about it. Yeah.
I think it'd be fun. Yeah, that is super cool.
Yeah.
Also, Wei, I was curious, do you have an example of like what the programmer needs to do to inject soft asserts, or maybe how this affects the development flow? Like, do I put this in CI? Do I run this overnight? Do I put annotations? Sort of what's the, like from the engineer fingers at the keyboard, what's the workflow like?
Yeah, I like this question because I have SE background. I was thinking from a user point of view. I think this work is motivated by some ML, experts. They're talking about how difficult to debug their code. So I think, during development, we can add in those soft assertions so they know their code has instability. They will change it even before the delivery. Definitely, it can be used for like checking the existing code already written overnight to report to the developer. Here's potential problems. Here's input can trigger the problem. Do you think it's feasible? Should you fix it? So CI could be used as a feedback to the developer running overnight. You can see the time to run the tool. At least so far, we see it's not take a long time. So I also think integrate directly to the desktop, the IDEs give feedback saying, here's the input. Do you confirm this could be a potential issues and realistic input? So I see those both. And also maybe during deployment, during training, if you have soft assertion deployed, you can terminate your code earlier. Some of the instability can cause the model does not learn. So you don't need to continue run another, 10 iterations. You can stop early. That could be another scenario I'm thinking of. Yeah.
Fantastic. If there are additional questions for Wei, people could please drop them in the chat. We will have a little bit of time at the end of this session, but I think we will go ahead and jump over to Nema next.
Thank you.
Yeah, thank you, Wei. This was fantastic. So let's see. I see Nema. Is a screen share?
Hello, yeah, let me share my screen.
Okay, so Nema Dagan is going to tell us about a random topic, which is very exciting. And yeah, there's a little disclaimer, so I'll let you make that. But I've been thinking a lot about random rounding, so I'm particularly stoked for this talk. Please, Nema, take it away.
Excellent. Yeah, thank you. And yeah, I don't know what was up with the slide advancing, but yes, I do have to start with a little disclaimer. This is all my work outside of Anthropic, and I'm not here representing Anthropic. So all the opinions here are mine and are not Anthropic's opinions. Moving on with that, I just wanted to give a brief overview of randomness libraries and the sort of current state of randomness and how I think we should extend correct rounding to this concept. And so randomness libraries are really a big block of numerical computing and are big in AI and ML, as well as some privacy-preserving cryptography. but they're not covered by Math.h because they tend to have some system assertions or system dependencies and so on. And they are split generally into two parts. So there's half of a randomness library that generates random bits, and the other half that turns those into usable results, so draws from a distribution. The generation of random bits mostly has to be done considered empirically, but we can start thinking about proofs of how to transform a known random bit stream into other things. And so I'm just going to abstract away the first part in this talk behind this gen bits function, and we're not going to think about it. And the rest of this is about how we transform a random bit stream into another form, and how we want that other form to look. And so when I sort of first looked at floating point random number generators, I was sort of surprised to see this. But it turns out there's a very common building block of uniform random floats in 0 to 1, which is just entirely always done by fixed point. And there are some issues with this that we'll get into, but they're not always done correctly as well. So the Go uniform random float generator sometimes returned 1, even though it promised never to return 1. And then they fixed that by just redrawing if you return 1. And so when we think about correctly rounded functions, they all tend to have an input and an output, and we intend for the input and the output to sort of match as though the function were computed at infinite precision and then rounded back. And so when extending correct rounding to randomness, I'm going to propose the following definition, that we assume that we do the random draw in infinite precision or in real number space, and then round back to floating point. And so that is how we want the algorithm to draw, or that's how we want the algorithm to run. So what that means is the integral on the screen. But if you essentially think about the PDF of the function being mapped over a floating point number line, we can just integrate in the spaces that round to any given number to figure out what properties of the resulting floating point stream we want. And this is a bit of a change of promise from previous libraries, which were a little more ad hoc about this. But it does allow us to prove a good number of things and come up with other sort of empirical tests about a good number of other properties that should give us a lot more consistency. So just to get on to comparing fixed and floating point to think about algorithm development. So the algorithm we discussed 2 slides ago draws from the number line on top and then maps to the number line on the bottom. And you can see that we're sort of missing quite a few outputs. Many of them are unreachable. And if we start thinking about that, the distance of the output distribution from the integral on the previous slide, it is actually quite far. And we can see this in tests that I'll show later. So how do we, just to move on, I'm going to now discuss an algorithm for drawing from 0 to 1, which is so far the only algorithm I've figured out in this family, but that I hope is much bigger. And we have these fixed point draws. So we're just going to do this in 2 steps and 2 fixed point draws, but it turns out that this is enough to get full floating point randomness. So our first draw is going to be a fixed point draw to find a real valued range. And then in the second step, we're going to fill in the missing bits. So first we find a range that shares a common exponent, and second, we draw the tail bits that we're missing. And the second step is actually rounding mode dependent, and we can start thinking about rounding modes because we have a rigorous idea of what randomness should look like. So in phase 1, we'll just draw from this number line and we'll find some number. And it turns out that if any range we choose other than the range starting at 0 will always share an exponent. And so if we find a range, we just proceed to the next step. If we don't find a range, we just have to do it again. So we zoom in and then we draw again. And we keep zooming in until we get to the subnormals, at which point there are no more ranges that don't have a common exponent. So we just have a recursive algorithm to find this. And then from there, we just backfill bits. And there are separate ways of doing this for directed rounding. If we're rounding up, we never consider the floor of the range as a possible output, but we consider the ceiling. And rounding down is the other way. And if we happen to be rounding to nearest, we have to split the difference a little bit. And so with this algorithm, we can then make we can make proofs and show that it turns out that the distribution of output is exactly the same as if you had done a real number draw from this range and then rounded to floating point. I have also done some tests of this full chain, and we can see one of the properties that we expect with when we think about the distribution we should get is that the LSBs should be uniformly distributed. And this is sort of easy to see from the floating point number line. So each region here is sort of equally spaced, or each region here has equally spaced an even number of equally spaced intervals. So within those regions, those least significant bits should always be uniform. And it turns out if we go through the method of division, by the time of hitting 10 million numbers, we basically have lost most of our precision of the floating point format. And we have a stream of numbers that is distinguishable from a random real number draw. And we can do this with many other properties that we come up with as well. One of the perennial problems with correct rounding is speed. It's gotten this reputation that correct rounding is slower. And in randomness, I really wanted to make sure that the library that I was beginning to write was no slower than doing random draws the normal way. And it turns out not to be. So when we see this test is with 2 bitstream generators from Go, PCG and Cha-Cha-8. And it turns out to be about the same speed to backfill the bits as it is to not backfill the bits. And we'll note that the zooming down step we mentioned here is vanishingly rare. And so just quickly, a few extensions. So this algorithm here is, I think, the first one of a set that I would like to make. And I've been starting work on extending to arbitrary ranges. And I think Gaussian random draws are also really interesting to think about in this framework. And there are a couple of interesting tools that seem to just work and help, namely doing things in interval arithmetic and then sampling later, and then also doing your full sample and then using stochastic rounding. But a few other things that are interesting to consider here is setting up some good benchmarks and test suites to show the difference between fixed point and floating point randomness. And I am also trying to figure out how to make sure that algorithms like this don't necessarily need rejection sampling and can complete in constant time. In conclusion, we have this idea of correct rounding for random functions, which is that we draw from the infinite distribution, or we draw from the real distribution and then round. And that lets us prove a lot of things. And that lets us have one uniform baseline for what randomness should look like. And I have code in C++ and Go, MIT licensed, and a preprint in GitHub of a random draw in 0 to 1. And I am planning to add more algorithms, and you're all welcome to contribute as well. So thank you.
Very nice. So there are a couple questions I see from Pavvel already. He's quick on the draw. One thing I was curious about, Nema, so you mentioned different, potential applications. Have you run, and you showed some sort of micro benchmarks on individual samples. Yeah. Have you run any end-to-end applications where you've swapped in, your new implementation?
So one thing that I've had trouble with is actually finding a good end-to-end application that sees sensitivity from its random number generator. So I actually don't have a great example of that, and I know they exist out in the wild, and I'm not sure where to find them.
So you saw Purva's talk, I think, at the end of last session. I don't know how sensitive the probabilistic programming workloads are, but I do think that crowd is pretty interested in correctness.
Yeah.
And, they are trying to do this kind of sampling. The rest of that paper that Purva was talking about, sort of increasingly interesting ways to sample from more intricate distributions. I bet that there's some connection there that might be worth sort of chatting. Purva had to run because of teaching, but I think that could be a good worthwhile connection to make.
Yeah, I agree.
Actually,
I had been looking at
go ahead.
scientific computing workloads, so I would totally believe that. Yeah.
Actually, my question was almost exactly what Zach was saying, but it is a specific workload that you might consider. I know in the applied math community, randomized numerical linear algebra routines are increasingly being adopted, and I suspect that your work would be very relevant to the quality of the randomized matrices that are generated there. And the applications are like solving systems like AX equals B, or doing least squares problems, or other types of these like big linear algebra core operations, but it's all with random matrices. So I bet there's something there.
Yeah. Thanks.
I was going to ask the same question. We're working on RAND-LAPACK, which is a randomized version of LAPACK. And the experience in the community is you can have very rough random numbers without losing, accuracy or convergence. So
yes. Yeah, that's definitely true. There are lots of algorithms that don't care.
So one thing we do care about, and I'm wondering if you've addressed this, is we want the random numbers to be reproducible. But maybe that's more of a problem of the underlying random number generators rather than your subsequent generation of them.
Yeah, that's fully a problem of the bitstream generator. So if you have a bitstream generator that's fully reproducible, the draws are fully reproducible.
Yeah, we figured out a way to do random dense times dense matrix multiply faster by reproducing the random numbers on the fly quickly enough.
Yep. Yeah, that's one thing you can definitely do. Yeah.
Pavvel also mentioned maybe applications in crypto.
Yes.
Are there places there where it's very important that the randomness is correctly rounded, or?
So I have seen this. I'm not entirely sure. I have seen several places in privacy preserving algorithms where people will construct this system of floating point that they've in which to do cryptography, and they do all these proofs about it, and then they use fixed point randomness. And so I think that is actually a pretty big application space, but I'm not entirely sure who or where.
Cool. This is fantastic. Okay, folks. Well, if there are more questions, please drop them in the chat. And I think we'll go ahead and jump to our last talk of the day for FPTalks 2025, which is our very own Pavvel Pancheha, who's going to tell us about TwoSum and making it go burr, I think, as they used to say. I don't know if kids still say that, but at one point they said make it go burr. So please, Pavvel, take it away.
Yeah, thank you, Zach. So the point of this talk is really the provocative claim in the title, which is that fast TwoSum is faster than TwoSum. And I'm hoping to take the next 15 minutes to justify this claim and explain why it's both less trivial than it sounds and also nonetheless true. So stepping back, I'm going to do the standard sort of floating point intro. This is a floating point number. So here I've got a 32-bit float, and I've labeled the initial implicit bit, and then there's a 23-bit mantissa. So we've got 24 bits in total. And of course, there's an exponent separately. And if you've got two of these numbers, you can do things like potentially you can add them. And when you add them, you align their decimal points, and then you do the addition. And as we know, when you do this addition, you might end up with more than 24 total bits set. So here, due to the alignment, we have 25 total bits set. And in general, you can get sort of more or fewer bits set depending on carries, how the alignment works exactly. And because our floating point format, 32-bit, can only store 24 actual bits, we're going to end up with all of these bits in yellow actually stored, And then there's going to be this final bit, this 25th bit, and we got to do something. So we'll round it off. Maybe we'll round up, maybe we'll round down, depending on your rounding mode. But at the end of the day, what's going to happen is there's going to be some additional rounding error. And one way we can think about this is we can think about splitting the true real number results that I have on the screen here into two parts. We can think about splitting it into the floating point output plus some kind of error term. And you can call this an error term. Sometimes people call it a residual, etc. And an interesting fact, a really cool fact, a really useful fact, is that for floating point addition, if you take a few mild assumptions about the size of your floating point format, assumptions that are true in practice, then this residual is an exact floating point number. So this is what's sometimes called an error-free transformation, or an EFT. We've taken our two inputs, the numbers above the line, and transformed them into two outputs. At all points in time in between, we've preserved the sum. So S plus E below the line is equal to the sum of the two values above the line. And coming up with algorithms to compute E is an interesting challenge, and what this talk is about. So I'm going to start with a simpler case. Then addition, I'm going to start with multiplication just to illustrate the basic idea. So here's how it works. Say you do a floating point multiply. Well, when you do that floating point multiply, it's going to do a real number multiply. And then there's going to be some error term that's lost. So here I've written the sum S, the floating point number S, as the real number product A times B minus an error term that got lost. And what I'd like to do is recover that error term. So here's one way to recover that error term, very common algorithm to do it. We're going to use a fused multiply add. And what this is going to allow us to do is multiply A and B without rounding error and subtract off S. So if you just work through the arithmetic here, you'll see that this computation recovers that error term E that got rounded off. You don't need to follow the logic in your head precisely. You can trust me that this works. But I do want to call out a few basic features of this error-free transformation algorithm. So first of all, we compute the floating point operation. That's step one. And then secondly, we compute this error term. And we do that by basically doing the original computation in like a slightly different way that lets us subtract off the first computation. So with multiplication, we have this fused multiply add instruction, and that lets us do a multiply and a subtract in like a slightly different way that recovers the error. So now let's take this idea for multiplication and look at how to do this for addition as well. It turns out to be like way more complicated. Here is a standard algorithm, and this one is called TwoSum. You can see a couple of the basic features that we had before. We are, again, first computing the floating point sum. So that's the first thing we do that's available right away. And then we do the computation and subtraction in a slightly different way. Basically, at a very high level, the way TwoSum works is it leverages the non-associativity of addition to kind of recover how much error actually happened. It's really not important that you follow the logic of this algorithm. It turns out that proving it correct is actually incredibly difficult. There's like a bunch of different cases to analyze based on what sign of what is equal to what. And it also depends on the rounding mode, whether or not it works, and et cetera. But it's a very cool algorithm. And maybe to give you just like something slightly lower level than just trust me, just to give you a little bit of the structure of this code, you can see that it's kind of made up of 4 blocks. The first one computes A plus B and floating point. Then we've got 2 blocks that basically compute kind of the error that we get because we have to align A and B at the decimal point. And there's like, potentially some truncation going on. And then we take those 2 errors and add them at the end. So this is this standard TwoSum algorithm. And these kind of algorithms, these error-free transformations, they turn out to be super important because they're building blocks for bigger programs. So one thing that you can do, you can take these building blocks and build upon them to estimate the rounding error for divisions and square roots. For division and square root, this rounding error isn't always exact, but again, you can approximate it using some algebraic tricks. You can also build on top of that. You can use more complicated algorithms to approximate the rounding error of operations like sine, exponent, log, arctangent. And the point actually of estimating all of these rounding errors is that you can use this to build multi-precision arithmetic libraries. Basically, you do an operation, you capture its rounding error, you keep that around in a second double precision number, and then you kind of repeat this process over and over again to do multi-precision arithmetic without losing information. And at least on some architectures, this is a really effective way to get high precision arithmetic. It can be really fast. I know that Fredrik said in his talk that actually this way is bad. So, maybe it depends on the architecture, but again, this is a very common thing people do. And so because these error-free transformations are these building blocks in these larger algorithms, we want these building blocks to just be as fast as possible. And that's what this talk is about. So let's start with multiplication. Let's look at how the performance of this works. On the left here, I have C or Python or something code. But if we compile this to assembly, we get something that looks like this. There's already something nice going on, which is that the negative S step and the fuse multiply add operation on modern CPUs, that gets fused into a single fuse multiply sub operation. So here, these two lines of code, they become two assembly instructions. And then those two assembly instructions, in an out of order CPU, we can't just think about the CPU executing one at a time. We kind of have to think about a dependency graph. So here's the dependency graph that this ends up looking like. Basically, the FM sub depends on the fmul. So you have to do these one after another, and the latency of them matters. And then if you look at how this is scheduled on an actual CPU, here I'm using timing numbers always from the Apple M1, because that's what's in my laptop. And on that chip, both the multiplication and the fuse multiply sub, they're both 3-cycle latency instructions. So this sequence of two assembly instructions ends up being 6 cycles long. And honestly, I think pretty easy to convince yourself that this is basically optimal. You're not really going to do better than 2 instructions to do 2 things. 3 cycles is the length of basically all floating point operations. It's pretty easy to exhaustively search the set of all 6-cycle sequences and show that there aren't any that are faster than this one. But now, let's look at addition. With addition, we've got a lot more instructions. Here you can see that they're all addition and subtraction instructions. So turning this into assembly is pretty simple. It'll look something like this. We're just using add and sub operations one after another. And if you look at the dependency diagram of these instructions, there's a little bit of parallelism that you can get. These 2 middle subtraction steps can run in parallel. And that means that you can probably schedule them on different execution ports in your CPU. So end to end, this is going to take 15 cycles, not 18, again, because we have those 2 instructions that are executed in parallel. And so basically the question that I asked myself is, can we do better than 15 cycles? And I think we can. And the way to do that is to look at this algorithm called fast TwoSum. Fast TwoSum has a simple logic to it. It says, assume that you know which of A and B is larger in magnitude. Or more precisely, what you really care about is the exponent size. If you knew that A was bigger, then the sum and A would have the same sign. They'd probably have reasonably similar exponents. And then you would know that the subtraction on this line is exact. And because you know the subtraction is exact, you actually know the value of all these last 3 lines of code. And that means you don't actually have to execute them. And so you have this much shorter sequence of instructions. So this is called fast TwoSum. It's faster. It has half the instructions. And if we do the math, we'll see that there's a dependency chain of 3. Slide says 15, but it should say 9. This is a 9-cycle latency operation. So fast TwoSum is faster, but there's, of course, a caveat. It's only faster because it relies on this assumption about which of A and B is bigger. And so can we remove that assumption? Well, we definitely could. One thing we could do is we could just check the assumption and swap the values if they're in the wrong order. And so if we want to do better than TwoSum, we want to ask whether we can do this swap in less than or equal to 6 cycles. So here's a couple of ways that we could do that. One way, the sort of simplest way, is to use a branch instruction for the if. And if you do that, you find that you are not adding any additional time except for this absolute value in comparison. You end up with 5 extra cycles, so that's faster than 6, but it has a risk, which is that the CPU is going to try to predict this branch, and if it ever mispredicts, you'll get 14 additional cycles of latency. So it's either 5 cycles, which is good, or it's 18 cycles, which is bad. So can we do better than this? Well, one way we can do better is to use these conditional move or selection operations. These don't involve the branch predictor. The CPU just executes them in a fixed number of cycles. And so if we look at how this will execute on the CPU, we'll see that these absolute values and the selections can operate in parallel. And so the way this gets scheduled is it'll take 6 cycles of latency. And that's still pretty good because remember, fast TwoSum was 6 cycles faster than TwoSum itself. So let's put that together. We've got scheduling that looks kind of like this. I've got this initial block here for the floating point add. I've got this swap step, and then I've got the last 2 steps of fast TwoSum. And importantly, the swap and the floating point addition can run in parallel. So I actually don't add a full 6 cycles. I only add 3 more cycles on top of an ordinary fast TwoSum. So this gives us 12 cycles of latency, and it's just as good as TwoSum. So that's the first claim of this talk. Fast TwoSum is faster than TwoSum if you do a branchless comparison and swap instead of doing it with branches. But you still might be wondering whether this is truly optimal, whether we can go faster. And that's a question of shrinking this gap. And it turns out we can if we just kind of reorder these instructions. Now, this doesn't quite make sense, but what we can do is we can speculate about which branch we'll end up choosing and do the ordering both ways. And skipping ahead a little bit, that's going to give us a dependency graph that looks like this and something that's going to schedule in about 11 cycles of latency. So that's basically the main claim of this talk, that by thinking carefully about how the CPU is going to schedule it, you can actually come up with faster instruction streams than TwoSum. The key is to use a branchless comparison for the fast TwoSum swap. And if you further do a little bit of speculation, you can save an additional cycle, giving you something like 20 to 30% speed up in the best case. Thank you.
Thank you, Pavvel. To kick things off, what about x86?
Yeah. So I used ARM assembly throughout this talk. On x86, things are a little more complicated because there's so many different ways to do floating point arithmetic on an x86. But like the only sane way is to use SIMD instructions. And there you likewise have a something called a blend. So it's like V blend VPD, I think is the instruction. All these SIMD instructions have these horrible names. And you can do the same kind of trick there. The one thing I will say, if you do this in assembly, it works great. So the same exact trick works on x86 and you get a similar kind of speed up. If you do this in C, I have found it much harder for some reason to convince the same compiler, but on x86 instead of ARM to generate these branchless instructions. Even giving like probability annotations, etc. So on x86, I think it is more important to handwrite the assembly. Whereas on ARM, I could convince the CPU by just like using the word volatile in a couple of places that it should generate the assembly that I wanted.
Nice. Nema has a question here.
Yeah, I asked in the chat if you have a comparison of reciprocal throughput.
Yeah, I do. So basically, the answer is all of these fast TwoSum variants have the flaw that they involve more instructions. And so if you're just executing a whole lot of these operations in parallel, then you end up just being bottlenecked on like dispatch from the dispatch queue to execution ports. So reciprocal throughput is worse. If you do kind of an offhanded calculation, you get something like 2.5 cycles instead of 1.5 cycles in terms of inverse throughput for these fast TwoSum variants instead of normal TwoSum. So yeah, if you're doing a lot of these in parallel, you may instead want to use TwoSum, or you might want to think about the critical path, use the latency optimized version there, and then off the critical path, use the non-optimized version.
Pierre is asking about an fmin fmax.
Yeah, that's a great question. I tried many times to use fmin fmax to do the sort faster. The challenge is you're not quite sorting A and B based on their values. You're sorting A and B based on their absolute values. So like you can take the absolute value and swap them swap the absolute values, but if you try to then use the swapped absolute values to correctly swap the unabsolute value ones, then you end up with like more cycles than just doing it with
you might,
compare and
I
swap.
think you'll find an absolute compare, absolute mean, absolute max.
Interesting.
Yeah.
Where?
Let me find it.
Okay.
While Pierre is searching, because maybe we'll be able to loop back to this. While Pierre is searching, Jim asked about propagating infs and nans through this code.
Yeah, that's a good question. The truth is that TwoSum behaves pretty weirdly with infs and nans to begin with. I think the fast TwoSum versions will do worse, but I'm not 100% sure. I didn't think about infs and nans when I was doing this. Jim, honestly, you know better than me what happens to TwoSum with infs and nans, so you tell me.
So we had a whole long paragraph saying how the new augmented edition should behave in the latest 754. So because it was complicated.
Yeah. Okay. Interesting.
Andrew has a question about doing a bunch of these in a row. I don't know if Andrew, if you want to expand on.
Just, if you do E for the second last one if you do E for the previous one in an array while you're doing S for the current one, then you get to overlap those two. And for a long array, it just takes n plus 1.
Yeah. It depends a lot on exactly how much you are overlapping. So you're kind of already overlapping the sum with the compare and swap and doing the tail of the fast TwoSum. It's true that the sort of latency for the float output is much shorter than the latency for the other output. I looked at doing C's like, compensated summation algorithm, for example, and you don't win as much as it looks like you should, because again, the critical path ends up being all of these error terms repeatedly stacked to each other. And the critical path for that error term is still, pretty much the same 11 cycles.
And that's with old TwoSum as well as new TwoSum.
Yes. Yeah. In either case, you end up with that challenge. So again, you win because you get 11 cycles instead of 15. But there's no sort of additional effects from the fact that you're overlapping these.
So I believe, by the way, the AVX instruction being alluded to is vrange PS and vrange PD. Batteries not included.
Wait, that's the instruction for what?
That is the instruction for taking a range comparison of it's a generic comparison operator that can do absolute values.
Okay, interesting.
Okay, FPTalks 2026, even faster TwoSum. Get ready. But yeah, and Santosh has a couple of points about Paul Zimmerman has shown some interesting use cases for fast TwoSum. I don't know if there's any more you want to expand on there for sure.
I actually I chatted with Paul about this, and I did try using these optimized TwoSums in his core math library. I couldn't measure any kind of win. I assume that the latency of the TwoSum is being overlapped with something else, and so you don't end up with as much of a win as you thought. Or maybe there's some effect from like the higher inverse throughput. Would love to explore that further, but those are much more complicated functions. There's like branches, there's memory, etc. So it's a little harder to understand what's going on.
Totally. Okay, folks. Well, thank you so much, Pavvel. I'm gonna pop the slides back up here. This has been a lot of fun. Thank you very much to everybody for showing up. Just wanted to mention, so we do this every summer. There's been some discussion on the advisory board and the community. I think we are strongly considering moving from July to August next year, in part to avoid the Pavvel deadline, but also to give a little more breathing room in between the end of the academic year and prep for this event. So if you have strong feelings about that, please get a hold of us, let us know. And then the other thing is there's these monthly talks as well, which are a longer format. So those are about an hour. And, we have a lot more sort of interruptions and tangents and side quests during those meetings. Please, feel free to join those. More the merrier. We also, thanks to Santosh, have a form up on the main webpage where you can always submit a proposal or suggest somebody that you think maybe we ought to reach out to come do one of these talks. So I wanted to make sure we highlighted that. Also wanted to thank all of the speakers again. This was a really fun day. I feel like I learned a lot, and it was great to catch up and see everybody. And most important of all, thanks to everybody who came. It was really great to connect and see the discussions going on across all of these talks. Please stay in touch. We did end up having sort of one less talk last minute. So if folks want to have a broader discussion, very happy to leave the Zoom open. But yeah, I think thanks everybody. Thanks so much to Pavvel and Ian, especially for doing a lot of work behind the scenes, getting this all put together. Yeah, it was great to see everyone.
Thank you.
Great to be here. It's now time for beer in the UK.
Yeah, we're coming
Thank
up
you
on
so
lunch
much,
here
Zach.
on West Coast.
Thank you so much to Zach for organizing things and emceeing.
It also, by the way, I don't think it's a secret, but it is Ian's birthday today. So all of these talks were Ian's birthday present.
Yes, it was very nice.
Yeah, happy birthday.
I'm gonna turn off the live stream and the recording in case anybody's been like sitting on something very spicy that they just didn't want to share on the record. How do you turn off the live stream? See, Harry.